Sounds good. So just going to start. Yeah. So first, thank you very much for having me here today. Yeah, I'm very excited about this opportunity today to talk about or research on learning to understand the world from video. And I would actually like to start with motivation for the kind of research I'm going to talk about today. So what you would like to do in the long run is to enable mobile robots, such as those that you can see here, to freely navigate out there in the open world and to assist us with daily tasks. And of course, for robots to do so, they have to first, they have to understand their surroundings, right? So they have to understand the static 2D scene geometry and its semantic meaning, so they can understand, for example, where drivable surfaces are. Just as important, they have to be able to localize individual object instances they might want to interact with. They also have to understand motion patterns of individual objects and anticipate their future motion. This is really important for robot navigation. Yeah, also it's really important that robots are able to localize themselves and their end destination in the map, so they can plan their trajectories ahead. And this is the task of localization. Yeah, so I'm actually really excited about all these research fronts, and we have been working on all of them. But today I really want to focus on the question of what is around me and how do these things move. And I want to talk about this from open world perception perspective. And also I have to say that compared to other problems, this is kind of the one where I'm least certain what is the right way to approach this. And this is also what makes this line of research so exciting for me. I'm really happy that I can actually present here today my point of view, and I would be very curious to know what folks think. All right, so what we ultimately really want to do is to obtain a fine-grained functional understanding of any concept in the visual world, right? And in computer vision, our successes so far have largely been driven by the supervised learning paradigm. But I think this is not really gonna cut it for robotics. And to illustrate this point, I'm visualizing here 30,000 classes that, according to this study of Biderman, as humans can recognize. So here in ImageNet, we actually cover quite many semantic classes. We have image level labels for a large number of classes, but this is not actually what we really need in robotics, right? So in robotics, we have to understand the 3D structure of objects. We have to understand how they move and how we can actually physically interact with them to achieve a certain goal. And then if you also look ahead in how robotics data sets look like, I'm just illustrating here example of Kitty that is quite widely used in autonomous driving. We have in Kitty labels that come in form of 3D trajectories with 3D bounding boxes for only a handful of object classes, right? It's much more expensive to label it. And of course, there are now newer data sets out there, but the number of classes they cover is still significantly smaller compared to what you get in ImageNet. All right, so I don't think that labeling is going to cut it, right? I think that robots have to learn to model objects by simply observing streams of sensory data, such as video, because this is also what us humans do. And I'm also going to argue in this talk that image-based object localization and tracking are going to be central to achieve this. So overall, we can actually set up this problem of learning from video in the open world as follows. So we're going to assume that we can collect image level labels for objects that are frequently observed, right? For those we are going to see often, and we can definitely label them. And then we are also going to have lots of unlabeled video that we are going to use. Now our goal is going to be to learn to model all objects that are going to appear in this video. And the one way you can think about this is that with classes that are frequently observed, and you can label them, you can train a general object detector. And then this way we can adapt this detector to new deployment scenarios, such as new city, airport, factory, and so forth. And in this talk, I'm actually really going to focus on learning to detect objects, but in the long run, you of course also want to understand the 3D structure of objects, motion patterns, and so forth. And I'm going to touch this at the end of this talk. Yeah, I was thinking actually about this problem already years ago when I was a PhD student, and I was really fascinating with this notion and with these papers that we can actually localize and discover objects by hypothesizing different plausible segmentations of images. So back then, folks obtained those with using bottom-up segmentation techniques. And I was also really excited about this this work that actually shows that if we have videos when you have some object that is centered and exhibits dominant motion, you can localize these objects and use crops of these video tracks to train object detectors for these objects. So I think this is really fascinating, but this is not really how the world that is the world observed by embodied agent looks like, right? It looks really more like this. You're going to have multiple objects. They're going to be occluding each other, and also ourselves, we are moving around this world, right? So to train new detectors for these objects, you're going to have to localize and track multiple objects through occlusions across time. And yeah, this is actually exactly what we've been working on. And early versions of our tracking methods for attacking this problem, and those we actually used as an input stereo video, and we used data-driven object proposal generation methods to initialize our object tracks. And then we derived from stereo video cues that to associate these object proposals over time and localize these objects in the 3D. Of course, in the end, you end up, with a 4D volume where you have a large number of object tracks that they may also overlap. So we did some optimization in the end to do unique assignments of object identities to pixels in the video. Okay, so this is a very high-level overview. In practice, this looks roughly like this, right? So on the top, you see object proposals we get from RPN, and on the bottom, you can see 3D sim flow that we derive from stereo. We use these cues to associate proposals over time, and this is how the output looks like. So for training this, we used a COCO dataset with 80 labels for 80 classes. Here on the top, you can see stereo, and on the bottom, corresponding images. All right, so we used these methods to mine video object proposals from existing datasets, right? So we would just then take datasets such as Oxford Robot Car, run our trackers, mine object tracks, and then we performed discovery. And what we did back then is we simply clustered these video proposals that we mined using k-means based on appearance features. And these cluster assignments then give you IDs, cluster IDs that we then just use as pseudo labels to retrain our base detectors. And then you can see here that detectors for objects, newly discovered objects such as these cones or these sign bollards appeared. And yeah, it was really exciting that this actually worked, right? So we could track null objects, group them, use these group ID as pseudo labels, and learn to detect new classes. But there were several challenges that we were facing. And one thing that is very obvious is that this only works for frequently occurring objects, right? So these sign bollards are not terribly impressive objects, right? But they are observed very frequently. This is why this worked. But this kind of defeats this purpose of this idea that we can label frequently observed objects. We actually need to learn to model rare classes from video. Another issue that we were facing was concern evaluation, right? So we really didn't have the right data sets for this, and benchmarks or even evaluation metrics. It's so for the overall task or individual components, and this way it's then very difficult to make progress. So for example, if we just talk about tracking, right? So we did make progress on this front. We could see that we track objects that are outside of the vocabulary that we used to training or RPN model. but we didn't have any performance. We didn't know how to provide any performance guarantees back then. Another issue was that this was also very challenging from engineering perspective, right? We had multiple networks, multiple components. This was slow overall, and then you kind of when you are, turning so many knobs, you run out of energy to innovate on more fundamental side of the problem, such as how to deal with the long tail. And actually, we did address these issues in recent years, and want to talk about how we did that. So here, I'm going to first lean into this long tail issue. And here, I will talk about how you can actually train a network in end-to-end fashion for joint object discovery and detection. And also ensuring that we can actually learn to detect rare classes in a self-supervised manner. And here I'm going to talk about this work that we presented at NeurIPS last year, but here comes a bit of a plot twist. So to actually simplify this problem, we here looked at image collections rather than videos. So now in the next minutes, I'm really going to focus on the images rather than videos. All right, so just a quick reminder of how to stage object detector works. I'm sure that folks are familiar with that, but I really want to make sure that we are all on the same page. So in the first stage, we have region proposal network. This will give us a list of regions of interest. And then in the second stage, you're going to take each region of interest or each object proposal. You're going to regress bounding box. We can also segment instance, not necessarily, but we can do that. And here I want to zoom a bit into this part where we then classify this region, right? And we do K+1 classification, which means that we are going to classify this region as one of the K objects that were labeled in our data set that we use for training or background. But if you really think about this, this is not the right thing to do, because you are also going to classify objects that were not labeled, and you cannot exhaustively label everything, right? You're going to classify these objects as background as well. We actually did here some rethinking, and what we really do in the end is we will classify each region proposal as one of K known classes or N unknowns. We don't know necessarily how many unknowns we have, so we're just going to set a large number N for this. And also want to contextualize this a bit with this very exciting line of research on open world object detection. So in open world object detection, there's this implicit assumption that you have some annotators that are gonna label the data for you, right? And then you're gonna retrain your detector. And actually, in this work, we address exactly that. So we are gonna train the network such that it learns to label the data via self-supervision. And yeah, now let's talk about how we can do this. So we're going to start with supervised training of faster or mask-RCNN using some label data. So you can really think about this step as take faster RCNN, take COCO data set, train. Of course, you have to do some modifications, but those are details. So in this step, we are going to train the backbone, we are going to train the region proposal network, and we are also going to train the regression hat. These components are, of course, class agnostic, right? And then we are also of course, train the known object classifier. And this is where the semantics really comes in. So this stage, we know how to propose objects, regress, and segment, and these are then components that we are actually going to keep frozen from here on. And we are really going to also rely on this notion that the network already learned to some degree how to categorize objects based on some label data, right? And actually, this is important point, and this point is nicely made in this paper from folks from Georgia Tech, right? So clustering is really it's really ill-posed problem. There are so many ways on how you could group your data. You could group them by color, orientation, and so forth. And the right approach here really seems to be to approach this also in a data-driven manner, right? So you kind of, if you have some examples of what is the right way to group, you can learn which features are not important for grouping, such as object color, right? So this is why we need some labeled data for this. All right, so we already have trained our classification head for k known objects, and now we are going to add a secondary classification head. And this one is going to be trained to categorize novel object instances. And you can really think about this as here actually predicting cluster assignments, right? This is one way to think about categorization. Now we can continue training this network end-to-end using unlabeled data, but actually in practice, we are going to use combination of labeled images and unlabeled images, right? So we're going to extract region proposals, then some region proposals are going to be matched to the primary head during training, right? So because we have some labeled data, and others are going to go to the secondary classification head. And then we're just going to concatenate logits from both. We are going to strap softmax layer on top and train everything using cross entropy loss. So we are going to be jointly training these heads. So actually here now comes the plot twist on how you can actually train this, right? So if you just look at overall loss, right? You have here region proposal loss, we have the bounding box regression loss. Here we have the primary classification loss, and here labels for this, of course, come from labeled data, right? So for k classes, and then we have this self-supervised classification loss for which we don't have labels, so we have to generate them, right? We're going to generate pseudo labels, and we are going to do that online while we train network for the current batch. And what this loss really encourages the network is to categorize every region proposal, and we also keep in this supervised loss that actually encourages known classes to be categorized according to the class vocabulary for the label data set that we use, and it's also going to alleviate forgetting, right? If you didn't keep this in, you will just forget how to categorize labeled classes. And this is how we actually generate pseudo labels. So we perform online clustering while we train the network. And really, if you think about this, earlier I mentioned we use k-means, but k-means is really not the right thing to do because, I mean, of course, first of all, it's slow, right? So this is one problem. But the second problem is that using k-means, you explicitly assume that your object class distribution is uniform. And we know that this is not true, right? It's object class distribution that really follows long tail Pareto distribution. If you think about this problem, you have B region of interest in the current batch, and we want to assign them to N prototypes that represent null objects. And this actually really is optimal transport problem. And we know how to do this efficiently, right? We can do this quite efficiently by Sinkhorn NOP algorithm, but it's going to be here very important to impose this restriction that the marginal distribution of assignments of region of interest to prototypes follows a long tail distribution as well. Otherwise you will have exactly the same issues as if you cross cluster with k-means. Yeah, so this is how we generate pseudo labels, and then given the current weights, we're going to generate pseudo labels, and then we're going to use these pseudo labels to update weights, right? So this works in alternating fashion. Right, so I want to talk now a bit about results. So first, at inference time, this is quite similar to vanilla faster RCNN. We have two classification heads, so we're going to push origin proposals through both, concatenate logits, and then we're going to get class assigned via softmax. And now to evaluate MAP. Okay, first I have to explain this. We used COCO labels for training, right? And we are going to use Elvis labels for evaluation how well we do on enabled objects. But to evaluate MAP, we do have to transfer labels to our clusters, right? Otherwise, we couldn't evaluate MAP. But this is the only part where we use these labels, right? Just to labels or clusters. And now if we look at the results, so going from COCO to Elvis, where we just train on COCO labels and evaluate on both. First thing I have to point out, so our method is RN-CDL, right? And compared to fully supervised method that is trained on full Elvis, of course, there is still quite a gap, right? This is not surprising because, in fully supervised method, we just leverage all labels in this data set. But compared with with prior work. This is quite a big step forward. And these baselines that I'm listing here are all adapted from the literature on null object class discovery in the context of image recognition, and they're all applied on the same set of region proposals sampled from RPN as our method. So this is really apple to apple comparison. But then there's also this interesting result that actually, if you adapt Elvis model on visual genome dataset, we actually get really close to performance that we get with fully supervised model. All right, so these are some key results. Here I have some visuals. So here, blue objects are part of COCO vocabulary, and red are the part of Alice vocabulary. So one thing you can notice here definitely is that there are so many more blue objects, right? This is because these are frequently observed objects. Rare are the rare objects. And here you then can see some example of objects that we discover when we train on COCO and go to Elvis, or if we train on Elvis and go to visual genome. Then I have here also some examples of the clusters that were not matched to any Elvis classes, right? But they're still, discovered clusters that cover legitimate object classes. Okay, so this was on how we deal with the long tail problem and how we can address end-to-end detection discovery. And now I want to get back to videos. So briefly want to talk about our work on open world tracking. So of course, this overall thing that I'm talking about is still very, very much active line of research. And I mentioned at the beginning that we need good trackers to track known and unknown objects, right? And this is exactly what we addressed in this paper, right? Because prior to this, we didn't really have a good way on answering how well we can actually track the unknown objects. And this paper really gave community all the tools to make also progress on this front, right? So data set, benchmark, and baseline models. So the key question that we pose in this paper is, of course, how to evaluate your open world trackers. And here we based everything on large vocabulary tracking data set called Tau. And one thing we did was to make clean cut between known and novel objects, right? So the known overlap with COCO vocabulary so that you can train your region proposal network on the COCO data set. And it was really important to make here a clean cut, because otherwise, and this I see often happens in practice, is that you have, for example, a car as part of your known object set, and then you have something like ambulance car or ambulance vehicle among the so-called unlabeled objects, right? But it's really defeat the purpose because they're same object classes. So really make sure that you don't have such weird overlaps. And yeah, we also propose this this metric here that basically tells you whether you are actually tracking relevant objects that were labeled in this data set, and we have really several hundred classes labeled in this data set. And this term tells you how temporally coherent your tracks are. And once you build the tools to evaluate trackers in open world scenario, then we can actually rigorously talk about results. And we did really very thorough evaluation, and I just want to distill a few key takeaways. So here, this part for proposal generation, we just used RPN, and looking at our data set, it really turned out that we can reasonably well recall unknown objects, right? But what was interesting is that we can recall very well large objects, but not so well smaller objects. So here we're still quite some gap to bridge. And of course, this limits how many unknown objects you can track, right? If you don't have proposals for them, you're not going to be able to track them. So moving on from here, we studied what is the right way to associate proposals, right? This is quite different compared to what other folks in tracking are studying. For example, pedestrian tracking in Mod Challenge, where you're associating the detections that come from a reasonably good object detector, right? So this is actually much more challenging. And what is interesting is that we came down in the end to a very simple recipe that basically tells you, for association, compute bounding box intersection over union between your proposals and tracks where bounding box from the last frame has to be motion compensated by optical flow, and you also should use cosine distance between second stage features from the pre-trained detector. I mean, it's a very simple recipe, but it worked quite more robustly compared to standard baselines that we could evaluate the scale, particularly from unknown objects. And what was really interesting is we evaluated then this baseline also on standard closed world benchmarks, such as Davis unsupervised and Kitty multi-object tracking. These are really different problems, right? And our approach was better or on par with state-of-the-art methods that were highly tuned and specialized for this particular benchmarks. And yeah, we could also visually verify that we can also track objects that are outside of the Tau vocabulary, right? So these objects that I'm showing here that we track are not even labeled in Tau, even though it's quite exhaustively labeled. So yeah, this is our current progress on this problem, right? So how to tackle the tail issue and how to do open world tracking. And I'm just getting to the end of my talk. And before I conclude, I'd just like to throw out a few things to think about. So one is, of course, what is the right classification granularity, right? There are probably infinitely many, but I would say that this really depends on your end goal or the end task. And actually here I just want to bring up this paper that probably no one knows about. It's a paper that we did years ago with my master student. And what we did here was we actually generate a database of tracks. We constructed 3D shapes of objects and their trajectories, right? And then and we cluster them according to shape and then according to trajectory, so that we could at inference time, make a lookup into this database first according to shape and then according to the trajectory, and we just optimize these clustering parameters so that it maximizes the forecasting performance, right? So this was the end task. So this is actually such an example of where we actually optimized the clustering for the end task. And yeah, for last slide for today. So another question is how you can actually here combine different sensor modalities, right? And earlier I talked about generating pseudo labels, right? And we said that we had region proposals that we assigned to end prototypes, right? And one thing you can do is, so we initialize these prototypes, or the features for these prototypes were initialized randomly, right? But it would make a lot of sense to actually use vision language models to initialize them. Then you make this problem already significantly simpler. Another thing that you can do is, for one region proposal, you can also, if you have autonomous driving data set, you can also get corresponding views of these objects from your camera rig, right? Because these setups are calibrated. Or you can also pull out LiDAR points that project to these region proposals, and you can then just extract features and add a constraint that all these views of objects have to be assigned to the same bin, right? So this could also be object track, by the way. So you could enforce that crops corresponding to the same track get assigned to the same bin. And this is how you can actually here in this framework connect multiple modalities. So didn't do this yet, just a few ideas on how one can do this. And yeah, this is all for today. I would like to thank you for your attention. If you have some questions, I'm happy to answer. Thank you.
All right, are there any questions? Comments here? I have a quick question.
Iqbal Mohammed from Samsung. A really interesting talk. So the work that you were talking about, the N novel categories, there's this challenge with like imbalanced data, right? For classifiers, and then we do class balancing and so on. So how do you kind of get the right N versus your K? Like are there balancing issues that show up?
So So I think that the fact that we still that our performance is still below the fully supervised approach could be due to balancing, right? And here it's really difficult to balance because you don't know your frequencies.
Yeah.
So yeah, when it comes to balancing, I mean, I think that implicitly you do some balancing because when you generate pseudo labels, right? Because you enforce that your marginals follow this long tail distribution. So this is the only way we can enforce some balancing.
I see. And then just another like separate topic, which is in terms of metric learning spaces, right? So in applications like, I guess, recognition, facial recognition, so on, they do metric learning, which ends up inducing a different kind of a space. And for novel categories, that seems like a reasonable approach, right? But the space that I think your method is inducing, it's not metric learning because you're using cross entropy at the end. So, I mean, you surely thought about that. How does that interplay as well?
Yeah, sure. Go ahead. Yeah, that's a good question, but I think I don't have very good answer to this. So we let me think how to
because I think it's a very, I really like what you're doing. I think there's a really huge opportunity for improvement. Maybe that's
Yeah, I totally agree with this, and I think that really the only answer I have for you right now is that we didn't get to explore this direction. But sure, contrastive learning makes a lot of sense. Actually, folks from open world detection community, they are definitely doing that. And I mean, one thing that was the case with our approach was it was sort of elegant in the sense that it nicely extends existing two-stage detectors, right? You just you just get logits for K plus N class in the end. You just do your softmax, you get your assignment, and that's it. But probably at the training stage, you could I see definitely a possibility to also add contrastive loss.
Thank you so much.
Sure.
Brian Cook from CVPR. So, question: like, how does your method handle, say, compound objects? Like, say I'm novel to this day, and I'm either a person or I'm a badge and a shirt and pants and shoes. And how do you decide sort of what level that granularity that it should find these novel objects? Is it in the distribution shape you have and the number of classes, or how's that too?
That actually comes directly from the parameter n. So depending on how you set n, you will get coarser or finer grained classification. It does turn out though that so remember we also did some experiments where we in parallel train this for different ends, and in parallel obtain different classification granularities. But this I would definitely say that it's the question is, of course, what is the right granularity, right?
Exactly, sort of its application.
Yeah.
I'm just curious.
Yeah.
Right expert application.
Exactly. And this is where what I was aiming at in the end. That I think this is really application dependent.
Thank you.
Sure. Thank you.
Hi, I'm Pablo from Just Office. So I was interested in the point you made about having a goal to condition how you're going to cluster your new classes or novel classes. So have you thought about using natural language to express your goal? So for example, if your goal is to find yellow objects, so you have a query, find yellow objects, and you find you classify your objects in that query. Have you thought about that?
So I'm not sure if I fully understood the question, but if I got it right, you're asking on if we thought using language models here.
The goal, your goal for finding objects.
So if I understood the question right, then what I was talking about at the end, that you can initialize your prototype features using language models, right? So you could say, for example, this is the list of objects that I would like to consider. I have visual language foundation models such as CLIP, and I'm gonna, based on this these names of these semantic classes, pull out corresponding features, right? That's and this models already align the text and images, right? So then this actually gives you initialization, initialized visual features for object that you would want to discover. So I think this is one way to approach this. But there are also so many folks working on this and so many other different approaches out there that, yeah, sure.
Thank you, Ben, Gosha. Great, Tom. Good questions.
Okay. Testing audio. Are we good to go, Sam? Okay, excellent. Thank you. All right, so like I said, these data sets obviously require a lot of cumbersome work to annotate them, whether that be using segmentation masks or category labels. And so because of this, they end up being usually limited and smaller than what we would like. In the real world, we have so many more categories and so many more objects beyond, for let's say our COCO data set of 80 object categories and so on and so forth. So the question we're basically trying to ask is, the internet obviously has a lot of data, and recently there's been this trend of using data with weaker supervision labels, essentially caption labels, and trying to train models like the CLIP model, which is a contrastive model, or recently the diffusion model for synthesizing images from text conditioning. And so the question we're trying to ask is, can we leverage these weaker supervision labels from captions to be able to do this task, discriminative task of segmentation, whether that be panoptic segmentation, instance segmentation, or semantic segmentation, and how can we go about leveraging this large amount of data? Obviously, like I mentioned, one of the challenges is that oftentimes the captions may not actually, represent or describe the object well, or they may be wrong. So, we have this weak supervision to deal with. So in the first work that I'm going to describe in our series is a work that we did, which is called Group VIT. This was a paper last year at CVPR. And here, what we were trying to understand is, whether segmentation or grouping can naturally emerge from these contrastive type models, for example, CLIP. And I will describe more of this work in detail. So we know that CLIP, for example, it has been shown to have really good zero-shot ability in recognizing or labeling categories of new objects that have not been seen in labeled data sets before. So it has very good zero-shot performance for object recognition. So we wanted to ask the question of, could we use this same idea? Could we leverage CLIP style models to also do zero-shot transfer to semantic segmentation? And is that even possible? That was the question that we were trying to ask. And here, I just want to make clear as to what the problem definition here was. The problem definition was, normally when you're training a model for semantic segmentation, you have ground truth labels available, you train your model with those. And so in this case, we're assuming that we have literally no ground truth labels at all. So it's fully supervised. And the question we're trying to ask is, can we train a model in a fully self-supervised manner without using any segmentation labels to be able to predict mask labels? So we proposed a model called Group VIT, and it was intended to exactly perform this task, which is zero-shot transfer to semantic segmentation with text supervision only. So what we did in this particular model was, so our goal was that you have a large amount of image and caption pairs that you've curated from the internet. And then we train Group VIT using a contrastive loss between the caption as well as the image. And what we find is that, the process of training Group VIT, these self-learned groups emerge, bottom up. It's basically bottom-up grouping. These groups emerge and they're semantically meaningful, which was really interesting. And then once we have these groups that emerge, we can then at test time inference a particular image, extract its groups, and associate the particular groups with an embedding we take text labels and we embed them, and then we can associate them with particular categories. And in doing so, we're able to basically be able to do completely self-supervised zero-shot segmentation. And so the hope here is that, this does not require any labeling, any kind of human effort whatsoever. So how did we achieve this? What is the architecture behind Group VIT? To do this bottom-up grouping, semantic grouping, which is at the core of letting these groups emerge. So we had a modified architecture to the VIT, and in the VIT architecture, or the visual transformer, essentially, as you might be aware, the basic idea is you divide the image into non-overlapping patches, you embed them into, you project them into a linear space. And so our key idea was that in a normal self-attention, you essentially compute in a transformer, you compute the cross self-attention between all the spatial tokens that are present in the image. So our main idea was to introduce a bunch of learnable grouping tokens. And the idea was that along with a special block called a grouping block, and the idea was that all the spatial tokens get assigned to one particular group. And these groups are learned in the process of training via contrastive losses with the text. And one trick was that, so all the image patches get assigned to particular groups. And now if you do sort of like you could do hard assignment to the different groups, or you could do soft assignment. And essentially what we found was it was important to do soft assignment as opposed to hard assignment. And we also used a trick that is very often used, for example, in VAEs, which is to pass the gradients through the pass-through trick to pass the gradients through all the way back to the transformer. So this grouping block essentially allowed us to group the image patches into first level groups or tokens, grouping tokens. And then we had a hierarchical structure wherein after the first stage grouping, we had a second stage of grouping where these smaller groups will be merged together into larger groups. And in order to learn these groups, I won't go into too much mathematical detail, but the basic high level idea was that, so normally when you train the CLIP model with text, what you essentially do is you take the entire caption and you embed it into a text space, and you compute a contrastive loss. So in a batch, you have a bunch of images and you have corresponding text corresponding to the images. And so the idea is that the similarity between the pair, between the text and the image pair that we know to be the given pair, should be the highest versus similarity between any other text or any other image in that batch. So we had a modified, so we used this contrastive loss for training our group VIT architecture. But in addition, we used a multi-label contrastive loss as well, wherein we extracted all the noun words from the sentence. And we had an additional loss where the noun word should also have a high similarity to the particular image versus any other images in the batch. So these were the three main components. One was to do this grouping block. The next was to do the hierarchical structure. And the third was to use this multi-label loss. These were the key three components to making group VIT work. And then at inference time, as I described earlier, essentially what you do is you take the image as is shown here, you pass it through group VIT, it extracts a bunch of groups that it has learned during the training. And then you have a vocabulary of classes, and then you embed those through, you create a prompt out of the vocabulary, like this is the image of a table, embed them to a text embedding, and then you compute the similarity and find the particular segment that has the highest similarity between the visual description, visual features, and the text features. So how did we do? So we compared group VIT to a bunch of different methods designed to do clustering or grouping of visual features. So for example, k-means clustering, mean shift, spectral clustering. And compared to all of these methods, group VIT performed significantly better by learning how to do this grouping through the learning process. And we also compared it to a number of other self-supervised. So these two are self-supervised learning techniques, Dino and Moco version 3, versus DIET. This is a fully supervised approach. And so what we did here is that basically, instead of using the VIT, group VIT backbone that we were using, we instead used these different backbones, replaced our architecture with a different backbone. And what we found was, again, group VIT did significantly better than these other self-supervised methods, and did comparably to the supervised method. And then the other thing we also tested was that we were obviously essentially modifying the architecture of VIT and introducing these grouping blocks. So we wanted to make sure that when these groups emerge, we don't accidentally lose the performance of object recognition, like the whole image object recognition that VIT or CLIP is designed for. And we found that we did not, in fact, lose that performance. And so here are some results. So in the first column, the second column here, we're showing the grouping at the first level of first stage of grouping, and then this is the second stage of grouping. This is the final prediction, and this is the ground truth. And you can see here that obviously, there's still a lot to be gained in terms of quality. Like the segments are not very crisp and clear. They don't follow the boundaries very well. The part of this also comes from the fact that we have a coarse granularity of the spatial tokens in the VIT. And so, but if you increase the number of tokens, the VIT increases in memory. So we all know that it's computationally expensive. And here are some more examples. And here's some examples of the Pascal context. And so, yeah, so this was really interesting and fun. And, we realized that using this text supervision, there's certainly some, there's a path forward in trying to sort of group these, semantic concepts together. We can sort of help it group all these semantic concepts together and be able to have a path forward for semantic segmentation in a zero-shot manner. However, the groups are not that high quality. So then we did not scale this up, but certainly the scaling it up with a larger data set is a potential way forward. Okay. So in the interest of time, I'm going to move on to our next work, which is a highlight paper at CVPR this year that we're going to be presenting on Tuesday morning. And this work is called Odyssey. And this is open vocabulary panoptic segmentation with text-to-image diffusion models. So here, this was a progression forward. And we wanted to ask the question, now we have these amazing diffusion models. Can we So this was kind of motivated by the fact that if you look at these text condition diffusion models, they're obviously very good at laying out scenes and, composing things. So the idea was that, their internal spaces must be well differentiated and they must understand what are, different semantic concepts. They're also correlated to text. And the fact that since they can lay out scenes, they must have some sense of where's the boundary or the segmentation boundary of different objects. So we wanted to explore in this work, can we use these large text conditioned generative models to perform open vocabulary segmentation? So here's a k-mean clustering plot of the internal features of the diffusion model. And you can see that they seem to be quite well differentiated. And if you contrast that with the k-means clustering of visual features extracted from, for example, a pre-trained clip model, they're not quite as well differentiated and separated as the diffusion model's features, right? So in this work, yeah, like I mentioned, we asked the question of, can we use these diffusion models to do open vocabulary panoptic segmentation? So we proposed this framework called Odyssey. And this is the meat, this is the main crux of what I want you to take away from this particular work. So how this model Odyssey works is you input an image, and this during training time. So we basically want to extract the internal features for this image using the diffusion, a frozen pre-trained diffusion model. So at test time, we assume that for a given test image, we're not going to have the caption available. So the diffusion model, as you might know, requires both the input image with noise added to it, as well as its caption, text caption. So we basically train an implicit captioner, which is essentially the image encoder of a clip model with an MLP added to it. And this, along with the features extracted by this implicit captioner and a small amount of noise added to the image, we do a single step diffusion process, the last step of the diffusion process, to pass it through the text to image diffusion model and extract the internal features for the image. We then pass these internal features to a mask generator. In our case, this is the mask to former architecture, but it can be any architecture. And this masked generator essentially gives us 100 different proposal masks for plausible objects in the image, and also gives us visual embeddings for each of those masks. To supervise these masks, we actually assume we train it on the COCO data set, and we train it using a binary mask prediction loss. Then the next task is how do you supervise this model to categorize these binary masks into various categories? And for that, what we do is we either train with the provided the category labels for each segment from the COCO dataset, or we use the captions for the images that are available. For the captions, we extract the noun words from each caption. We pass it through a text encoder, which is from the CLIP model. And then we take the dot product between the visual embeddings from the mask generator and the text embeddings of each of these category labels. And then we either use a cross entropy loss when the labels are available, or we use a grounding loss when we assume that we're using captions for training. And then during inference time, we do the same thing. We have a given image. We extract its implicit text embedding or implicit caption, and then we extract its visual features from a pre-trained diffusion model. We then extract different proposal masks from it. And then we also pool the features from an image encoder of the CLIP model to get another set of visual embeddings for the different masks. And then we have a vocabulary, which is an open set vocabulary, which hasn't been seen during training. We pass the names of the vocabulary through the text encoder and then compute the similarity matrix between the visual embeddings and the text embeddings. And in the interest of time, I'm going to go quickly. You're welcome to go through the details there in the paper. And then we associate the top matched category text embedding for the category label name with the visual embedding to get the various objects labels. How did we do in terms of performance? This is a performance on the ADE 20K datasets for the PQ metric as well as the mean intersection over union, and compared to mask clip and OpenSeg, we significantly outperformed these two previous methods. The other thing I want to note is there's a recent work called SEEM, S-E-E-M. We actually perform equivalently, comparably to them as well. This is unpublished work. I think it is under review at the moment. And here are some qualitative results on the ADE 20K dataset. And several of these categories, they're open vocabulary, they're not present in the COCO dataset, they're new categories. And we also tested on the EGO 4D dataset qualitatively. Here's some results. The code for this is also available on our GitHub repository along with a pre-trained model. We also have a demo on Hugging Face, which you can try out. And that is pretty much it. Just like to thank all my collaborators across these two works. Primarily, the work was done by Jari Shu, who is a student at University of San Diego, UC San Diego, California at San Diego, and a number of other collaborators from NVIDIA. And with that, I'm happy to take any questions.
Really nice. Both works were fantastic. I have a clarification question about group VIT. So the groups that you are putting in that are learned at each stage, are they sort of corresponding to the categories, or is this something more like a distribution? You mentioned that you're doing like a soft sort of assignment, which made me think it's more like discrete, like they're representing discretes. And how many groups do you pick?
Yeah, those are great questions. So we generally, I forget the exact numbers, but the general idea was to pick more groups in the first stage, so that to have a more coarse sort of grouping. And then in the second stage, and I think we have ablations as to what was ideal, but I believe we had 64 in the first stage, and then we had 16 in the second stage. With regards to your first question about whether those are semantically, so interestingly enough, even with sort of weak supervision coming simply from the caption, as well as from the multi-label supervision coming from the noun words of each caption. Even with that sort of weak supervision, semantically meaningful groups emerged. That was the interesting part, right? Like, you know, generally you would expect them to just be based on just low-level visual features like color or texture. But interestingly enough, semantic relationships kind of did emerge. That said, it was quite weak. You know, in the second work, what we realized was we were actually training with the available training set segmentations, right? So what we realized was if you have some data that's labeled, it's better to use it because then you get really good segmentation boundaries and the system learns how to segment things better. However, both these works, and I think this is where I would love for the community to work and take this forward, is the correlation between the text embedding and the visual embedding. That is where things are not ideal in terms of that matching. And I think that comes from the fact that the clip space, which is what's used to match the visual to the text, is not perfect and it's not ideal. That's my instinct behind it. I don't know if that answers your question.
No, it's very insightful. Thank you so
Thank you.
much.
Other questions?
Hi, nice work. I'm curious if you know if these ideas can be applied in the area of medicine. For example, where you have cases rate images and you have the reports written by a radiologist. And so you want to leverage this weak data, weak supervision to identify these different labels in the image. Like, do you know if this can be applied in that way?
I absolutely think it could be, because I think in the medical domain, I would imagine that I'm not an informed person to speak about the medical domain, but I would imagine that the number of categories would probably be somewhat more contained if you're perhaps looking at, a particular medical problem. And I certainly think that that would be a great place to actually apply this, because you can then use limited data sets that are hand labeled and then generalize to open categories that are not labeled at all. So I think that's actually a great place to try this.
Thank you.
Great work. Thanks for
Thank you.
sharing. My question is also about the group VIT. So in the training, there are various groups of pixels. So if there look like kind of correspondence the norms and the group.
Yeah, the correspondence is very weak. It's only coming through the contrastive loss. There is no explicit correspondence. Whatever it is learned.
Unmute. Start the video, everything. Really? Oh, that's. All right. Welcome to this talk. Thanks for the invitation. I'm going to talk about recent work we did on vision and language as a broad space. In my group, we do several things, and we especially like to explore multimodal tasks that require a deep understanding of both images and text at the same time. I am fond of constructing new interesting tasks, datasets, and benchmarks that we release periodically, especially trying to challenge current models, trying to make them fail with these tasks. We also look at other aspects, especially what are the limits of large language models. We're going to look at this today, and how are label spaces related, which is perhaps the main topic of the workshop, and whether we can do localization annotations for thousands of classes. So here is the material I'm covering. There is pretty a lot of archive there because lots of stuff that's very, very recent. In fact, half of this talk I never gave before. We'll see how it comes. The first is encyclopedia QA. And let's start with a trial. You guys, what city is this tree a symbol of? And when was this lighthouse fully automated? Any takers? No? Don't tell me you don't know. Really? You want to be beaten by a language model? Nobody? Nobody? Well, good news. Pali from Google doesn't know either. It does it completely wrong. He says this, but in reality, it is the answer. Large vision language models, we see later Rosa Palm and others, they really have trouble with this encyclopedic knowledge. Questions about detailed properties of fine-grained categories of or instances, because it's very difficult, even if they saw in the training set, and they did see this in the training set, it's very hard to memorize the details in the model parameters. Also, sometimes these models produce wrong answers without any explanation. So if you're a user, you get this answer 2000, yeah, sure, what do I know? Maybe it's right. The way to solve this recent trend in the language community that's slowly coming into vision is to do retrieval augmented models. That is trying to give the model the ability to access a knowledge base, and then, in this case, Wikipedia, where the answer is light, and then reason upon the text to solve it. And that will also solve attribution. The problem is that we don't have a good data set to challenge models in this direction. The popular OKVQA data set claims to require knowledge not visible in the image, and that's true. But primarily, this is common sense knowledge, like people that sit on a mobile scooter that trouble walking. Only 18% of the questions require very specific encyclopedic-like knowledge. So there are plenty of other data sets. I focus on those that are the most famous, and you can check the paper for more comparisons. And what we try to do is to build a new data set called Encyclopedia QA, which is specifically designed to challenge on encyclopedic knowledge. All our questions, 100%, are about detailed properties of fine-grained categories or instances. Like, how old does this reptile become? Huh? That's what you always wondered in the morning at breakfast. How old does it become? The answer is 40 years old. We even have multiple hop questions that require thinking beyond one document, like what amusement park is located in the city where this square is located, to figure out the city, figure out the amusement park, and requires more documents. We provide a control knowledge base with free-form text knowledge base, which is Wikipedia, where the answers are attributed to a specific piece of text. This would be for the Gila monster. And we release that knowledge base along with the dataset. We care about scale, making it in the million range questions. And for this, we come up with what we think to be clever ways to use annotators, automating nearly the whole process and leaving only very specific things we don't manage to fully automate to ask humans to annotate. It's a truly multimodal dataset. The question text alone is entirely meaningless. How old does this reptile become cannot be answered from the text alone. You cannot cheat. There are too many reptiles. When was this lighthouse founded? There are too many lighthouses, all founded in different ways. So we use for this the trick, this plus supercategory trick. We will return to this. So if we know that this is the Gila monster, we can ask about this reptile at a higher level, and that makes it extremely likely that you answer it from the text. So here is some examples of our questions. And we build on Google Landmarks v2 and iNaturalist as supporting datasets that provide us with the query image and also the ground truth category C of the main object in the image, which we don't tell to the model, but we use it to build the dataset. So here is how we build the datasets. So we have single op templated questions where we start from these basic level categories like monastery, these fine-grained categories like monastery. And then we write templates which we then ask the raters to answer, like who founded this, when was it founded? And this is truly multimodal by design because every combination of image and question as a different answer because there are different monasteries. Then we don't ask the annotators to solve that. Too difficult. You saw, guys, you couldn't do it. I couldn't either. Instead, because we have the ground truth category, we show the correct Wikipedia page to the annotator, who then only has to answer the question in the context of the correct page. He doesn't need to do the indirection of figuring out the monastery. So this is much lighter on the rater. The problem with this approach is that you only have a limited number of different questions because you have to template them, write them down, and we spent ages coming up with questions. So here we're going to do better, and we came up with automated question generation. We start from the Wikipedia page of a particular fine-grained category, like the Akasha Paradoxa, and then we can run a large language model, VQ2A in this case, which reverses the statements and turns them into question-answer pairs. That's fully automatic. And then you get very specific questions like, how many feet tall does the Akasha Paradoxa grow to? Which is more unique than what you could write by templates. You get more diverse questions, more questions with a valid answer, and at the end we ask annotators to check whether the automatically generated question and answer are correct, because of course you cannot trust large language models, can you? But with this approach, we get many more diverse questions, many more questions that have a valid answer compared to the template, so it's a high yield. And for the annotators, it's really easy. This is very quick. One thing that you need to do when you do this, you need to replace the Akasha Paradoxa with these three. And this trick we are going to revisit later. We ask a language model actually to do it. So these were single op questions that require finding one document in the database to find the answer in. But now let's do two op questions. So can we build questions that require two database pages? So for example, what is the main competitor for food of this animal? This animal is a lion and the main competitor is spotted hyena. You can now take the spotted hyena as a bridge entity in between and ask a question about the hyena. Like, for example, what is population size? If you combine these two, you can get a very natural question, like what is the population size of the main competitor for food of this animal, which is definitely contrived, but it's interesting as a test. Maybe it's not what you always wanted to know, but it's interesting as a test for a language model. So now, how do we get this combined question? That's also an interesting task, and we ask a language model to do it. You can actually ask Palm, show him the two sub-questions, and ask him to chain them into one combined one, which is a fun thing to explore in the paper. And the annotators, they never know that there exist two op questions. They are completely unaware. They answer the two single op questions independently, and everything else is automated. It makes it much easier. If you ask an annotator a combined question like this, his brain crashes entirely. So as I said, to make this dataset interesting, we need to replace the particular fine-grained category name with this plus super category. And for that, we also trained a language model. We prompt engineered the language model to do it, which is also kind of fun dataset construction trick. So here's the statistic. We have about 1 million image question answer triplets, really 221,000 unique question answer pairs. And then for every one of these, we pair with 5 images so that we have some diversity. And so, of course, this is the largest set of this kind. And I'm going to show some interesting results. So first of all, how well do language models do on OKVQA, which is a standard for so-called outside knowledge question answering? Well, it turns out that Pali, off the shelf, fine-tuned for question answering, and having seen lots of data from the web, does really well on OKVQA. In fact, it's state of the art, better than retrieval augmented models like Cat and Reveal. This is kind of sad for the retrieval augmented community. And the problem is that the data set itself can be answered too well by common sense and just logic. Now let's see. This is the ideal candidate to test it on our data set, see if I'm really right that it's harder, and boom, it crashes down to 13%. So good news. You might say, but I don't want PAL, I want something bigger. What about GPT-3? Everybody loves that. In Palm, 500 billion parameters. Well, they crash as well. Of course, in this case, those two models don't take an image as a part of their input. So basically, the 20% you can achieve is based on memorization and the ability to exploit tricks in the question formulation. But the conclusion is encyclopedic knowledge questions are really difficult for foundation models, just really hard. And now, can we augment them with visual retrieval? Ooh, I think that I give a little hit. Okay, very fragile. So now what we can do is to take the image, pass it into Google Lens, and that will try to retrieve likely images that are of that particular monastery. And then from the metadata around, you can conclude the name of the monastery, which you can use to go to on Wikipedia, retrieve the page, and give it to Pali or Palm or GPT-3 in their prompt as context. And you can do even better. You can do another trick that's fun. You can tell, well, you know, this Wikipedia page is so big. It's so difficult to think in that space. The language model is so tired. Maybe we can ask the language model itself, where is the answer? So now we break the Wikipedia page into sections, and we prompt the language model by saying, do you think the answer to this question is in this section? If he says no, we say, you're off the hook, throw it away. If he says yes, we ask again, hello, where is the answer? And magically, that actually works better than giving him the whole article against any possible information theoretical argument, given that it's the same information. You can help language models to reason. And the results you get are quite nice. You can get almost at 50% on our data set with this. And the remaining margin that's missing, there is analysis in the paper, is due to failure of retrieval. If you retrieve correctly, you can get up to 89%. In conclusion, I showed you a data set on detailed properties of fine-grained categories and instances that truly challenges foundation models like Pali, PAM, and GPT. And the way out to solve such challenges is a retrieval augmented component, which doesn't solve the whole thing. It leaves headroom for quite some research, given that we're not even at 50%, especially the two hop questions are very difficult, and I kind of hidden them away during this conversation. So this was the first paper. Now I'm going to talk about video localized narratives. Who heard of localized narratives? No one? Very good. Cool. Then check out this video. This is a still image localized narrative. It is supposed to be sound. Oh no. You want sound. People on Zoom has sound? Well, too bad, because this is supposed to be about the voice. So I'll play the narrator. Ash color, long sleeve, length shirt. This woman is holding a black jacket. Okay. Basically, we ask annotators to caption an image when moving their mouse while talking. So because they move their mouse while talking, due to the synchronicity, you get localization for free. This is something we did 3 years ago, almost, in 2020. Of course, this localization is not a bounding box super tight. It's some trace in the middle of an object. But it's very efficient. In 30 seconds, we get something like 37 words. So you can download this, and we have 850,000 localized narratives for free on our website, or at least since a while. This is widely used, especially to pre-train language models. You get really long caption, 37 words on average, versus typically 10 to 12 words in Coco or Flickr 30K. Now, images are cool, but videos are better. So check out this video. See, this dude is taunting the ostrich, showing him food but not giving it to him. The ostrich at some point decides to take matters into his own beak, steals the cup and eats it. Can we tell the story of this video with localized narratives? And the answer is no. Because if you let an annotator talk while moving their mouse on a video, there is no way to do anything else than following the one salient object that they like, probably the ostrich here, or the food if they're hungry. They're not going to tell the whole story. And if you have 6, 7 objects moving at the same time, how do we do this? So we spent quite a while. It took us, lots of people asked us to do video localized narratives, and we kept saying, we don't see how we can do this. And then finally, after talking to lots of people, we came up with a protocol that works, which is to ask annotators to watch the video, then select the main actors, in this case, the man and the ostrich, and some keyframes that are characteristic for that actor's storyline. And then separately for every actor, we ask them to speak while move their mouse. So in this case, they would say something like a man wearing a black shirt is holding a cup of food, and so on and so on. And then we repeat the story from the ostrich viewpoint. And this is good because the keyframes avoid the race against time. In a relaxed environment, annotators can annotate. We focus on the story of the video from the viewpoint of each actor. And if you have multiple views, then you can do all kind of fun language games and crossing between them. We ask the annotators to mention the actor name, its attributes, the actions it performs, both on the other actors, like the ostrich, and on passive objects like the cup. And this one narration per actor has the added advantage that you disentangle complex situations. In the dataset, we have stuff like with 5 monkeys jumping on a banana at the same time. And of course, what you get are words that are localized in space-time. Here is what we built, 50,000 videos. This is all available on our website. There is some sound I hear. 3 million words. Oops is particularly interesting. Is the set of fails, 10-second long videos of fails, which really show stories. UVO and OVIS are video segmentation datasets that show lots of things running around, and it's useful because you get the segmentation masks. So the annotations are really rich. We are talking 75 words per narrative. It's really a lot of detail. And we have various manual annotators checking the data. It's 97% semantically accurate, which means that the words that are spoken correspond to things that are actually in the video 97% of the time. And the mouse trace, we improved the ability to localize the mouse trace on the actual object compared to the still image version, and it's between 73 and 93% accurate depending on how you want to measure. And here is some distribution on 3 of the datasets. You can see that our dataset has more words and more diverse word types than compared to the closest related dataset ActivityNet. And here is an annotator at work, a bit cheated. I cut the breaks. Again, there should be voice here. Anyway, you can see the correspondence on top. Is moving the mouse pointer. The ostrich is looking at the piece of food held by the man. And suddenly, no, this is the man, sorry. Suddenly grabs the cap of food. Okay, this is much better with actual sound. And starts eating. So here I cut off the breaks, the annotators do it even slower, which allows us to localize objects really well because they take their time to do these very clean traces. So we also propose 2 tasks along with this dataset. Video narrative grounding. Here, because we use video segmentation datasets in 2 cases, we can pass by the trace segment to match the nouns to the segments. And now the goal is to localize from model to localize each noun with a segmentation mask in each frame. But because there are multiple identical nouns like parrot and parrot, you need to disambiguate them using a context provided by other words. Like this is the green parrot with a red black neckline. The other is the other parrot. And with just a noun alone, it's just impossible. So it's an interesting visual language task in this sense. And we made this for 8,000 videos. And compared to the closest related task, RefVos, we have 3 times more objects. And it's more difficult because you have multiple identical nouns, whereas RefVos can be often resolved just from one noun. And we also built a referformer baseline based on another network, which is a good number to beat for you guys so that you can cite us and tell us we did it wrong. We also built a second task on top of the localized narratives, which is visual question answering. We ran a model to reverse the statements made by the annotators to turn them into questions and answers. And then we ask annotators to verify that this question answer can actually be answered by that text. So it's really high quality. Questions like, what is the shape of the girl's hat? And it would be cone. These answers are just textual, but we also have location output questions, which are unusual in VQA datasets. Because we have the traces, we can ask things like, where is the girl that is wearing the pink dress? And from the trace, we derive a spatial-temporal bounding box that you need to match if you're the model. We also built on referformer and Pali to provide baseline numbers that you guys can try to beat. So this in conclusion, we made video localized narratives after 2 years of finally thinking how to do it on 50,000 videos. We also proposed a benchmark on top of it in case people want to use it as a test. Many people will use this data just for training, but it's okay. And if you want, it's all available, inclusive and pretty visualizer there. So this brings me to the next part of the talk, pointless labels on OpenImages v7. So this is work by a guy in my team called Rodrigo, and he was always saying, can't we get to a point where we have localization annotations in images for thousands and thousands of classes, not 200-300 like OpenImages or 80 for Coco or at best 1,000 in Elvis? Can we get really 10,000? So be ridiculous. And I told him, well, you know, if you ask people to draw masks, that's not going to happen. He said, well, maybe we can just ask them whether a point is on the object. That's very cheap. We can go to a mobile phone. You can do it on your mobile phone now because it's on our public crowdsource campaign. And then I told him, well, but you know, but which classes will they be, Rodrigo? You know, yes, you can click, but on what? Do you have a dictionary of 10,000 classes? And he goes, no. And those, how do you know they are on the images? Because, you know, you come with a dictionary of no pixels. So we thought, wait, we have localized narratives, which were already free form. There is certainly a lot of good data there. So here is how to build a large class vocabulary bottom up without defining it ahead. So the idea is to focus on tangible, so touchable and common classes. We start by extracting name and entities from the localized narrative captions, and then we filter them for tangible and commonly known entities. We don't want to have things like the very specific species of spider or so, something common. So extracting name identity is easy. NLP tools, here it will be image table and camera. And then this gives, from the 675,000 localized narratives in open images, this gives about 54,000 entities that are triggered this way, and we match them to the knowledge graph. And that contains beautiful, really useless things like Great Britain, Aerofurcata, which is the name of a spider, and Chinese folk religion, which is a concept, you can't even see it. So here comes the idea that in text, there are 54,000 entities that Google knows about. Good. Not good enough. So can we make them common? We use as common definition the North Oxford, New Oxford American Dictionary, so that very, very specific species of spider or products like Twix or the Eiffel Tower are not in there. That sends you to 40,000 entities, and now you can ask whether they are touchable, physically instantiated, and you can ask that in the knowledge graph there is a tag. And this sends you at the intersection into almost 6,000 whopping candidate classes, completely emerged from annotator behavior, bottom up. Nobody decided what the names are. And now we can pass them on to an interactive machine-assisted annotation process, which is also driven by localized narratives. I skip these details. That then produces these point label annotations. But because of the topic of this workshop, I decided to focus on the language part. And this sends us to OpenImages v7. Hope you heard of OpenImages before. It's 9 million images CCBY. There is a core set in it that is densely annotated. We have 60 million image level labels over 20,000 categories. That's a lot. 60 million boxes over 600 categories, 3 million relationships, almost 3 million instance masks over only 350 classes, and lots of localized narratives. You see, things with localization annotation, they're not that many. They go to about 600. But now, in our new V7 launch, we had 24 million pointers and labels that span over 5,000 classes, between 5.2 and 5.10, depending exactly how you want to count. And also we added additional corrected click points, so points that were derived from the instance segmentation process. And this leads us to a grand total of 66 million point labels on 5,800 categories. So this is certainly the largest dataset with localization annotations. And point annotations cover really many classes. This is an example image with ice creams, and these are all the classes covered by the points in this image. So it's really a lot of stuff. And you can also try to visualize all the data types we ever made in, this has been a journey of 7 years doing OpenImages. If you visualize the boxes, the masks, the localized narratives and everything, you can see an image that's so covered with annotations. My dream is that one day I can stand here before you and you don't see the image anymore. There's so many layers of annotations. That would be the dream. So you will say, yes, this sounds cool, but we want masks, we just want points. This is not accurate enough. So our next step is to pass the points into meta sum model. That's supposed to be very, very good at producing masks. But even just with points we show in the paper, you can use them not only to train segmentation models just from points, but you can also use them to evaluate segmentation models very nicely. So I now go to the last technical part of my talk and then close with some advertising. So now we move on to a work which is about finding label relations across data sets, an obscure topic that we all like to pretend doesn't matter in computer vision, but it is a problem. And I was so excited to see that this problem is highlighted in the workshop definition. So different data sets have different label spaces. So far, so good. But how different really are they? They have different set of class labels, yeah, sure. But everyone has their own visual definition of each class. We're going to see here some nasty cases. And the image is a sample from a specific distribution. Even if we agree on what a car is, maybe you have front cars and the other guy has interiors of cars. The protocol of annotation is distinct and different groups of human annotators have different biases. The visual meaning as a consequence of a class label, because of these arguments, depends on the data set. In the EDA20K, sofa and the Coco couch are actually the same visual concepts, although they have different words. And here is a nasty case where EDE20K distinguishes between tent, where you camp, and awning, which is more like what you use to protect from shade on a shop. Whereas both are called tent in Coco. So now the fact that awning is a child of tent, but tent is also a child of tent, that's going to be tough to do with language alone. And then there are cases where things are overlapping. EDE20K floor contains full floors carpets, but also full floor wooden floors. And Coco rug merged, where if the rug covers all floor, it's also ID20K floor, but if it's a pickable rug like a doormat, well, then it's not ID20K floor. And a wooden floor, it's not a rug in the other data set. So now you have these overlap cases. They're very nice. So the goal of our work is to automatically discover these relations, overlap, parent-child, identity, between labels across datasets without manual annotations. So we can understand better the relation datasets. When you have this, you can try to unify the label spaces and therefore train a single model on multiple datasets cleanly. We will also see other applications like identifying missing aspects and automatically fine-graining datasets. So here is the problem formulation. Technically, there are two datasets with their label spaces. And the output is to find out for every pair of labels, bipartite, are they related? And if they're related, then identity relation, a parent-child relation, overlap. And I'm going to try to convince you that this cannot be done with class names alone, because the meaning, visual meaning, are specific to the dataset pair. It depends how the dataset was constructed. So the method that worked the best for us was visual relation discovery. Here we train a model on dataset A, and then we apply it. This is a segmentation model which classifies pixels, and we apply it on instances of class B in dataset B. So now we can think of it as a conditional probability that this is on the animal is a cat according to the model trained on dataset A. So we look at all the animals and we see how likely they are to be cats. Now you can do the reverse. You can train an animal model on dataset B, apply it to the cats, and see how likely is that each of these cats is actually an animal. So this thickness of the arrows indicates the average probability over all the instances. So now you can just do the average in the two direction, threshold it, and that tells you how likely they are to be related. And this will give you some bipartite matching graph with various thicknesses. So now can we try to classify these relationships into the types I discussed, identity, parent-child, and overlap. So there you can do it with simple set theory arguments on how many instances are included in the other. But the thing that works a little bit better is to look at score asymmetry. So if two constants like couch and sofa have a very high mutual conditional probability score in the two directions, they're likely to be in an identity relation. But if they are in a relation, but one of the two probabilities is much higher than the other, they are likely to be in a parent-child relation. Like every cat is an animal, but not every animal is a cat. And overlap can also be found by reasoning combinatorially over these instances, but I skip the details. We also try to do it purely with language by mapping classes to the WordNet hierarchy and looking at distances over this hierarchy. Interesting, you can even find the overlap relation this way. So two classes like car and truck can in an overlap if they share a common descendant like minivan. And then you can do various tricks on this hierarchy to conclude these relation types like you can see in the paper. So we try to evaluate experimentally this. To evaluate experimentally, you need to define ground truth relations. We start from the MSEC dataset by Lampert and Colton, and we enhance it to be really accurate on these relation types. And then we can evaluate whether our automatic relation discovery actually manages to find these things. This is just binary discovery in this slide without the type of the relation. And the conclusion you can see from these plots is that from the visual relation discovery is better than purely linguistic, which is very interesting. The class names alone cannot solve the problem. And the combined linguistic and visual actually works best. And if you want some numbers, these are average precisions of reconstruction, and the combined vision language alone is always better than either alone. Combined vision language is better than either language or vision alone, and vision is always much better than language, which is very interesting because it means really there is a problem with the class names. And here is some example of these problems. Welcome to this festival of horrors. Mini bike is supposed to be different than motorcycle. It's supposed to be low till the one knees. But in fact, in ED20K, all the motorcycles are actually labeled as mini bikes. So there is a problem with the names. There is a problem with overlap. In ED20K, a stove is principally the cooking plat, and if there is also the oven, they add to it. In Coco, it's the reverse. An oven is principally the oven part where you put in stuff, but if there is a stove on top, it also included. So in some cases, like here, it's both stove and oven, but this one is stove without being an oven, and this is an oven without being a stove. So you are in an overlap relation, which we discovered automatically with our method. Here is famous tent and awning example. So the ED20K, the Coco tent is a parent class to the E20K tent. So 10th parent of 10th, it's impossible to discover with language, but we defined it here. And sometimes there are problems because the annotation protocols were not tight enough. Like there is circular dependency we discovered with our method between CRT screen, computer, TV, monitor. These are all things that semantically is slightly different, but the way they were annotated is inconsistent. And in fact, we discovered that within ED20K, labels are not mutually exclusive. So this is really a problem if you want to evaluate algorithms, because they might say monitor instead of CRT screen, and they were right. So 2 more applications and then I'm done. You can also increase label specificity. You can use the discover parent-child relations to derive fine-grained labels for parent instances. So you could take ED20K animal and try to subcast it into birds, cows, and others, because you discover that bird, cow, and the others are actually children of animal. And you can even find missing aspects. For instance, between Coco car and BDD car, we projected them all into an appearance space, clustered, and then analyzed the clusters, and we found that there are some aspects of the notion of car, although they both mean car, there are some appearance aspects of car that appear only in Coco or only in the drive, and sometimes aspects that are shared. For example, this cluster here shows cars behind a sports field that only appear in Coco, while the single front wheel view of a car appears nearly always only in BDD, which is a driving data set. And night driving scenes also appear only in BDD. And these cars parked behind a sports field makes sense to appear in Coco, but not in BDD, because when you're driving, you don't see such a scene. You're not driving in front of a sports field. So in conclusion, I show you a method to automatically discover relations between labels across datasets. Vision-based models outperform language-based model. The combination is best, so you really cannot solve it only with language. There are very subtle ways in which label meanings vary across datasets, which we illustrated. And there are various applications I show here in the paper even more. This brings me to my last 2 slides, which have nothing to do with language, but they're fun anyway. We are releasing 2 large-scale datasets of 3D reconstruction annotations. Here is over 100,000 object alignments in 3D CAD models that are aligned over videos that lead to a coherent reconstruction of the whole scene, which you can use to train 3D deep learning methods. And on the same videos, we also annotated structural elements like walls, ceiling, and floors, and then therefore you have a really complete full 3D scene reconstruction benchmark that you can play with. This I'm finished, and I have questions.
Hi, really great talk. I have a question. When you are going through the annotation process yourself and the folks that did the other data sets that you're talking about, there's like a set of instructions that you're providing to your annotators, and it's complicated. I appreciate that, and it's done in examples and it's done in stages, and sometimes it's not, coherent. But at the end of the day, like as the field moves forward, does it make sense to sort of codify that in some way, and then perhaps the specification that we give to our annotators can be a kind of key signal that can, help us combine in the same vein that you're doing?
Oh, I see what you mean. Codify, like written it down in a formal manner.
Yeah, that's right.
So that then when people want to combine 2 data sets,
that's right.
idiosyncrasies are kind of written.
That's right. So I work for Samsung, right? We have bill of materials. If you make a change, you document it, and as you're going through the engineering process, it needs to be very regimented. And it seems like that would benefit from in the annotation process as well, but nobody does that because it's,
So at Google, especially for open images, we are extremely strict. So we really write down, for the 600 classes where we made boxes, we literally had 600 slides. We wrote every aspect, this is a fountain, there is a water is part of the fountain, and the flame is not part of the rocket, and really very tight. But we never released that, that's true. I think your proposal is clever if it goes along with the encouragement to release to the community that, maybe in a standard format. That would also help. Instead of being surprised that a tent is not an awning, people would then get it up front. I can certainly take this advice and do it for my own data sets. I don't know if I can force everybody else to do it, but maybe it would be more about a movement in the community of trying to get more rigorous about explaining how we annotated our data sets. And it's not only about category definitions, it's also about what happened across the various validation stages. So how was it verified, in which way?
Right.
It's a good suggestion.
So it's one other thing, because it's, slides, right? They're extreme. It's like language. Language is efficient because it's imprecise, right? And for annotators, we need to be precise. So it's sort of like, at least my experience discussing with annotators, sometimes we show them examples, they do something, and then we look at it and we're like, okay, this is not right. So how do you, again, even that slide, do you have codification?
Yeah, this is a very good question. Few people care to this point. It's nice to hear. So at the scale at Google, like in this VQA game that led to 1 million, and on open images, where at some point we had, 60 million boxes and 3 million. So at that scale, it doesn't work anymore. That you sit there and look if the annotator did well. We had 80 annotators in the hands of my team for 2 years, and these 80, they kept going on holiday or being sick.
Yep.
So there were maybe 200-300 people in the game. You can't look at them. So you need to write automatic qualification tasks where an algorithm checks. And it's not that difficult. It's boring engineering. So if you know that the segmentation mask has to be here and not there, you let them segment, and then you look at IOU overlap. You master this. Just by hand, looking if they're doing fine. They do fine today, tomorrow they forgot it. So automatic training is necessary, and golden questions are necessary. Golden questions is when you drop questions you have an answer of in the middle of, and then you check that they're actually keeping up the standards. We do all that at Google, and it's possible to do all that on Amazon as well if you are disciplined enough.
Very cool. Thank you so much. Very insightful.
Hi, Brian Clip with Kitware. So I'm curious, when you're doing this alignment of labels between two data sets and looking for their matching, if you could use the output of that to measure the domain shift between those two data sets, if you've looked at that at all. Yes,
there is also an aspect of domain shift. Absolutely. It could be that you're meaning the very same thing, but everything is a little darker. Or so we have explored a little bit that into another paper, which is called Total Transfer, where we took around 30 segmentation data sets at the whole image level, in that case. Classification data set at the whole image level, and segmentation data sets at the level of a box around the object. And we did all kind of games of trying to match distributions and look how far they were. Nothing that worked today. The conclusion of that paper was pure analysis. We didn't try to have an active element that would then determine and say, it's like this. But if you're interested, you can check it out. It's called Total Transfer.
Total Transfer, thank you.
Thank you for the talk. I have two questions. The first one is about the last one and related to his question, I think. So when you try to use this method, proposed method to find the relationships between the classes in two data sets, then when you used it for transferring the knowledge in one data set to make a larger data set, for example, you have one data set and you want to make it larger by merging this additional data set, you use this proposed method.
You can use this method to guide you. For example, you can say, I now want a coach detector. I pull in all the sofa examples from Coco because it's okay, it's the same thing, right? That's how it can help you.
Yeah, so when you test it when you compare to your method to the vanilla merger method algorithm.
Oh yeah, sure. So we did not run that particular experiment, but I refer you to the great work of Colton and his team on the MSEG dataset, where they actually defined correspondency between a few datasets by hand for the purpose of doing a merger, and they show that the set union model, it's maybe not necessarily better, but it's more domain generalizable. It's a kind of upper envelope over all the scopes of the others. So that's very good work. And in fact, that work inspired ours because we thought, oh, can we do this process automatically?
Okay.
Yes.
Yeah. And the other question is related to, it's about the first walk.
Encyclopedic VQA, my favorite.
Yeah. So the model is trained on the questions, artificial questions. And also it is tested on the questions that are generated in the same way, right?
So artificial questions, what do you mean exactly?
I thought they are generated automatically.
Oh yeah, but from the Wikipedia text.
Yeah.
So,
but my question is they are generated from the statements, ordinary statements into questions, and then and when they are tested, they are also tested on the same kind of questions. But have you tested them with the questions in the wild, actual human questions?
I see. Okay, so because we have this templated and automated question, the templated ones, they're written by a human. It's really like a for loop. when was this monastery founded? Pair this with all monasteries in the dataset. And sometimes the answer is not on the Wikipedia page. That's why we need to verify. So some of them are natural. The automated ones are also there. So in any case, so in a way, it's important to say no in a positive sense. So we really wanted the answers to be in the knowledge base. So that's very subtle. So I could test the questions in the wild because there is one aspect of it that's interesting is that the question formulation will be more diverse. We can see about the language, but I don't want to lose a part of it, which is questions in the wild often don't have the answer in the knowledge base. Maybe you want to know how many monks lived in that monastery. And that answer is not on Wikipedia for that monastery. So for me, it was important for us to see the language model. We wanted to assess two things. The language model alone, with visual language model, with PALI, with image, it doesn't manage to answer out of memory, but it could potentially answer if only you could look at the Wikipedia page. So we wanted to check that gap. Now, if he goes and finds the page, but the answer is not there, it sends me into a difficult evaluation protocol. So that's why we didn't do that.
Yeah, I fully agree, but like I'm just wondering like how we can guarantee such a model can be like used for the to answer questions that actually have like that actually require some knowledge in the knowledge base. I mean, which we can actually retrieve like in your method, for example. Then like, but it's still in the wild. Like there are questions in the wild, right? In the like questions in the wild still like can have.
No, you're totally right. It could very
right?
well be that a human will phrase the question. It's the same semantic, but it will phrase it in a way that's farther from the way that you can find the answer in Wikipedia. And then can the language model go that semantic distance? I don't have an answer today, but it's a clever point. And I'm wondering maybe we could, maybe there is some annotation campaign we could do to obtain such in the wild questions. It's good.
Yeah, thanks.
Last one.
Hi. Sorry if you've maybe answered aspects of this question before, but so the first data set, the Encyclopedia VQA, my understanding was that if you could perfectly retrieve the right Wikipedia page, you could get 80% accuracy, right? So does that mean that if you had a perfect image embedding, which could perfectly search Wikipedia, that you would get 80%?
So this is very subtle. I think even with a perfect image embedding, you don't manage. The reason Lens managed is because it goes beyond image embeddings, right? So if you only look at Wikipedia images, there are so few of them. You need to be lucky enough that one of those is close to your query, close in the embedding space. Lens does beyond that. It's not only an excellent embedding, but it can use as bridge all the images on the internet. Maybe the monastery picture in Wikipedia is from another angle, is very different than the query. But on the internet, there is some in-between view. And through that jump, it manages to retrieve. Just based on the embeddings, this experiment not in the paper, we never managed to go past something like 10% top one retrieval. Lens is somewhere in the 50%, 60, something like this. So it is, the retrieval part is really hard just based on query to Wikipedia.
I see. Okay. Thank you.
Right. Well, thanks for allowing with the question answers. Thank you.
Sorry, I was muted. So yeah, it's my pleasure to announce the winners of the first OmniLabel challenge. The third place winner of track C is Sang-hyuk Chu and Bo Hyung-han. Congratulations. The third place winner of track A and B is Xiaowen Zhang, Zitao Wang, Yi Zhou, Yu Ting Wang, and Li Chong Zhao. Congratulations. The second place winner of track A, B, and C is Shan Tuyen Fran from Applied Artificial Intelligence, sorry, from Deakin University. Congratulations. And the first place winner of track A, B, and C is Liunian Harold Lee, Zi Do, Nan Yun Pong, and Kaiwei Chang. And Harold will give us a talk today about the method. Congratulations. We appreciate all the participants for their great efforts, and also congratulations again for all the winners. So among the winners, Harold and Sang-hyuk will present their work. I think Harold is already in Zoom.
Yes.
Yeah. Okay, I'll stop sharing. Harold, can you share your slides?
Yeah, sure. Can you hear me?
Oh, I think you're muted.
We don't see anything here. I think I'm not muted. Can people in the Zoom hear me? Do you have a speaker or something on? Yeah, I think people on the Zoom can hear me. Oh, sure. Should I begin? Wait, should I begin now?
Harold, can you try to say something?
Okay.
Yeah, we can hear you. Yeah,
okay, good. All right. Yeah, thank you. Okay, so I can get started. Right.
Yeah.
So I'm very happy to present our work. We call it DISCO, learning object recognition with rich language descriptions. Okay, so we've studied this class of models. We call it language-based recognition models. And I assume many people are familiar with the line of work from CLIP, where they use the idea for image classification. So you pre-train on a lot of image text data set, you train the model to predict which image aligns with which text. And at test time, you can do this zero-shot transfer by just simply query CLIP with a simple query, say like a photo of your class name. And the model gets very good zero-shot performance to a lot of benchmarks. People also extend this paradigm to even more dense and fine-grained tasks like object detection. So here I talk about one of our prior work, GLIP, where we take the idea to object detection. So now we unify the task of object detection and phrase grounding. So now instead of predicting from a fixed vocabulary, we teach the model to directly align entities mentioned in your prompt to regions in your images. And then at test time, what you can do is you just write in your prompt what you want to detect, and the model will detect those classes for you. But in prior work, in both CLIP and GLIP and many other work, the main kind of language query we actually test is mainly just a simple class name or concatenation of class names with a very simple prompt, like a photo of cat. So we actually question, can the model take more complex language queries? So the first use case we're thinking about is we can teach the model to generalize to novel categories. So for object detection, we consider the benchmark of Elvis. So you can see example, you want to distinguish this kind of a sweets. One is called eclair, the second one is called tart. And the baseline model glib cannot actually cannot distinguish the two. They think this is both eclair and tart, while our model, which I'm going to introduce, can actually distinguish these two based on the rich descriptions we give to the model. And the second use case, we were actually, when we're developing this work, we're searching for benchmark. So we're very happy to see that OmniLabel actually deliver this. So you can actually use language to specify your custom detection needs with instructions. And this include both generalizing to novel categories or even this fine-grained category like chocolate donut. So why cannot current models do this? So the first challenge is very easy to see. Fine-grained descriptive queries are rare in your pre-training data. So on the left, you see a typical image caption paired with this image, a toy bear holding a mallet. So so people actually have this reporting bias that we don't write obvious things. We see a mallet, we write the word mallet. We don't mention the shape, the texture, the subparts of mallet. Okay, so the solution is very simple. You can use large language model as a common sense engine to generate descriptions for you. So you ask, given a caption, you extract the entities and you ask, what are the useful features for identifying mallet? And GPT-3 give you a description, mallet is a kind of tool, wooden handle, etc. And the thing is, we actually didn't tailor the descriptions to fit the style of OmniLabel. We did this to at first to improve performance on Elvis, but later we'll find our model actually transfers well to OmniLabel, even if the description style may not necessarily match. Okay, so the first challenge seems easy to solve, but the second thing we observe is that can we simply present the description at both training time and inference time? We simply train the model on entity plus description data. Does this solve the problem? The challenge is the model is not incentivized to read the descriptions. So we actually find the model learns two kinds of shortcut. First is entity shortcut, and second is format shortcut. I only due to time constraint, I only talk about the first shortcut. But before I talk about that, I first give an example. So here is a very hard test case. So you given that image, you give two descriptions. The first one is a kind of tool, wooden handle with a round head. So this is the description for mallet, but I don't explicitly give the name mallet. And the second one is a kind of tool, long handle, sharp blade. So this is actually description for X that doesn't appear in the image. So a good model like ours should detect the word tool in the first image and suppress the second negative query and does not give boxes there. But you can see the glib actually hallucinate and just the detection is all over the place. Okay, so how do we solve this context insensitivity problem of glib? So recall that our training objective is mainly the contrastive learning objective, that is training the model to distinguish positive and negative queries. So now suppose now you follow the vanilla way, you give the model entity plus its description, and you ask the model which query aligns to the image. The problem is that to distinguish these two queries, focusing on the center entities is enough. The non-entity part of the query doesn't affect the label assignment of the regions. So the model can simply choose to memorize the alignment between entities and regions and ignore any descriptions you give. So the solution is very intuitive. We try to create this Winograd style query, like I show in the test case. So what you do is you remove the entity actually from the query, but you only give the description and its general type. And you ask your GPT to actually come up with a confusable object that's also of the general of the same type. So now the labels of the word tool now depends heavily on its language context. So the model is forced to read your descriptions. Okay, and you can also do this for training on caption data. So before it's a toy bear holding a mallet, you create some Winograd style captions. So first is a polar bear holding a mallet or a toy bear hammering a mallet. So you can change the verbs, the adjectives, the relations to other nouns. Okay, so now the label of the word mallet now also depends on its language context. Okay, so here's another example of how our model works. You're given this image and the positive caption is a clown making a blue animal for pretty lady, or the second one is clown kicking a soccer ball for pretty lady. And as you can see, our model can suppress that negative caption, but for glib, it doesn't know which is correct. And this kind of hallucination is actually very, very very, very important for doing object detection because you have to suppress the negative queries. And the experiments, we do it on Elvis and OmniLabel. So thank you for the organizers for introducing the OmniLabel challenge. So on Elvis, you can see we actually have, so the setting is same as glib. You train on object 365 and some grounding data and caption data. You do not use any Coco or Elvis training images whatsoever. So this is different from the traditional Elvis setting where you train on some base Elvis categories. We use this because we also want to test some domain transfer ability of the model. And you can see zero. So this is all the benchmark is zero-shot evaluation. So you can see on glibtiny, you get a 20 AP on rare categories, but our model improves it by 10 points. That's very drastic. The tiny model of our Disco glib actually outperforms the larger model of glib large and even grounding dino large. And then fiber, of course, we see some also huge improvement here. And on the OmniLabel challenge, especially prominent is the AP description. So you can see the APD here. So it improves from 16 to 21 here as well. And the final version we submit to the leaderboard was additionally trained on Ref Coco. But we can see actually our fiber original setting was already strong enough to for the challenge. Okay. So yeah, so with that, I'll conclude my talk. The takeaway is we want to tackle object recognition with very complex language queries. And there are many use cases for that. And challenges, you first need to get a lot of data that's very descriptive. And second one is you actually have to make sure your model make use of the information provided in the query. You can scan the QR code for our paper. It's not out on archive yet. It's on my homepage now, but we'll put it in archive. Okay.
All right.
Any questions?
I have a question. Do you?
Harold, can you hear us?
Oh, yes, I can hear you now.
Do you somehow verify the negatives that you generate with GPT are valid, or how do you do this?
Oh, yeah, that's a very good question. So for this kind of so we have two kind of negative. The first one is more about description for entity. We hope that we think we didn't do a very thorough verify. We mainly eyeball the examples, and we think most of them make sense. For the caption, indeed, sometimes you introduce some false negative there, but we think the majority are still good examples to learn. Yeah, but we totally agree. There is some noise when you use this kind of GPT models, and I think there is a recent paper that actually talks about you can use an algorithm to filter out those bad descriptions or bad features that GPT gave you.
All right, thank you.
Thank you for the question.
Okay. So thanks. Again, we're gonna skip the next winner presentation. We have a pre-recorded video which we're gonna put on the website. So let's have a brief break, and then after the break, I think at 45 or 20 minutes, we're gonna have our next two invited speakers, Alexander Schwing and Philip Trimble. All right. See you in a bit. The only things I found like, well, yeah, that's true. The OKV or the OKV.
I really tried. My main contribution is on outside knowledge. What outside knowledge? Probably off the shelf. What we go. Yeah.
That's not.
Yeah. Hopefully.
Yeah.
Actually, it's not that. I actually did that.
Here we go. He's the guy I have. Right. On the VQA stuff.
Yeah. Victoria. So yeah, please have it in your hands.
Yeah, we have like university. Yeah, absolutely.
I look forward to seeing
You
especially that the speaker is. Hey, I show the door.
He is remote.
What?
Alex is remote.
Oh boy, after the pandemic, I so much more enjoying those like or listen to that.
Yeah. But good with you. I hope.
Can you check? Wait. There's just too much. You check it. Alex is.
It's here. No, I can see the. Sorry?
Only one door.
Or did you reply to you? Ah, direct message. Okay, okay.
I think it's the same.
Yeah. No, he directly replied to me.
Oh.
But yeah. You can.
Can you guys hear me?
Yes, we can
All
hear
right.
you.
Great.
Hello, can you hear us?
I can hear you guys, yes.
Awesome.
That looked easy.
Yeah, surprisingly. We can also see your slides. Amazing.
That's good. Do videos actually work? I should have a ton of videos in there. Actually, maybe let me move forward quick. Let's see. Can you guys see that video on the top right-hand side?
Yes, we can.
All right, excellent. Great.
Do you
Looks
have
like all is working.
Do you have audio in the videos? No.
I do not have audio in the videos.
Great, that's nice.
Just to keep it simple.
All right, I think we should get started.
Sounds great.
Let me introduce you real quick. All right, welcome back everyone, also on Zoom for the OmniLabel workshop. I'm now delighted to introduce our next speaker, Alexander Schwing. Alex is an associate professor in the Department of Electrical and Computer Engineering at the University of Illinois in Urbana-Champaign, UIUC, and he's affiliated with the Coordinated Science Laboratory and the Computer Science Department. Prior to that, he was a postdoctoral fellow in the machine learning group at the University of Toronto, collaborating with Raquel Urtasun. Alex's research is centered around machine learning and computer vision. He is particularly interested in algorithms for prediction with and learning of nonlinear, multivariate, and structured distributions, as well as their applications in numerous tasks, like 3D scene understanding from a single image. Today, we are really excited to have Alex speak at our workshop. Now, without further delay, let's hear from Alexander Schwing.
All right, thanks a lot for the intro, Sam. Two things. One, I need to apologize that I can't make it in person. We recently welcomed a newborn to our family and he got somewhat sick, so I didn't want to just run away. So sorry for that. Thank you. Number two, title on the website says TBA. So I'm going to talk about TBA, towards basic or universal architectures for open world semantic segmentation. Here we go. I should also mention that much of this work has been done or is done by an amazing set of talented students. I usually refer to them as the magicians, and they are really the ones that deserve all the credit. So credit goes to them, I take the blame. Now, I guess it comes as no surprise to anyone if I'm saying that computer vision and machine learning have been remarkably successful in the last couple of years. Many models work very well. For instance, if we look at image classification or object detection tasks. Also, semantic segmentation. You can see some outputs of recent models at the bottom of this slide, and they make arguable mistakes. For instance, referring to the desk in the image on the left-hand side as a counter, or missing a street lamp or predicting a street lamp that seems to be visible at the top of the image on the right-hand side. Similarly, if we're looking at tasks like video object segmentation, these models perform remarkably well detecting and tracking and delineating and outlining objects. But if you look more carefully, are we really doing that well? How about heavy occlusions or frequent distractors? If you look at this arguably very simple model, pretty much all, and maybe I should pause the video here at some point in time. Not doing very well on this. Pretty much all the models fail to track this rather simple roller coaster. Similarly, if I continue playing this video and we're looking at these cats, yes, they're jumping back and forth, but as a human, we have no issues really keeping track of the cats, but many models seem to struggle with it still. Or in spirit, similar to, I guess, what this workshop is all about, how about us looking at text guidance? And if you look at models like the one illustrated here, there's an image input and expressions like the toy motorbike or the wheel of fortune. The wheel of fortune is pretty much entirely missed. And similarly, this excavator here, clearly, I think we ought to be doing better than the results that are shown here, or this skater with a colorful beanie and a scarf, and a skater with a black cap and a red scarf being kind of mixed up. So what is really missing? And I think that's what I'm trying to answer as part of this talk. And that's why I'm very excited about this OmniLabel workshop and really want to thank the organizers for putting it up. What we really need to do is we need to go beyond the simple category names that we have looked at in pretty much the last 2 decades. And also go towards text understanding and understanding referring expressions. Now, before I dive into those topics, I want to take a step back and start with very basic object understanding. What's the goal of what I'm pretty much talking about here is to essentially partition an image into segments associated with a set of categories. For instance, the image that you see here on the left-hand side gets partitioned into sky, building, tree, wall, grass, and plant, which is something that, as you might guess, we have looked at for quite a while. In fact, we started with semantic segmentation in around the 1980s. Obviously, we have made big progress since then, but the task has been put forth back then. There were a few more recent tasks that were introduced. For instance, instance segmentation came up around the 2010s. Panoptic segmentation, even more recently around 2020. And obviously the same thing for videos. Video instance segmentation a little bit later than image segmentation. Image instance segmentation around 2015. Video object segmentation also around 2015. And I've shown you the video beforehand already. And video panoptic segmentation also very recently around 2020. Now, if you look particularly at semantic segmentation, the approaches varied, but can probably be roughly categorized into 2 groups, I would say. In the 1980s to 1990s, semantic segmentation was usually formulated as perceptual grouping. In the late 1990s and also 2000s, we shifted from grouping towards more classification-based approaches, first with simple Bayesian classifiers, and then with more increasingly intricate classifiers, boosting algorithms, random forests, support vector machines, and random fields, conditional random fields. In the 2010s, we again shifted kind of back towards perceptual grouping using mask proposal algorithms like CPMC, O2PR, and then SDS, CFM might be some abbreviations that might be familiar to some people in the room. Since 2015, we shifted again back more to fully convolutional networks, which essentially classify pixels more or less independently with a convolutional neural network. Now, what's even, I guess, maybe I shouldn't use the word worse, but what also happened was that the space of methods got somewhat more fragmented. So for semantic segmentation, as we just saw, we looked at pixel classification techniques like FCN or DeepLab. And if you look at other tasks like instance and panoptic segmentation, they went a somewhat different route and stuck more with the object proposal-based methods or even mask classification-based methods. And despite the tasks actually being quite similar, having to group pixels, the methods fragmented into different directions. So what we were really after is this single, as I called it, universal architecture then that can address all these tasks. And that brings me to some recent work, or a series of recent works that we looked into with a couple of students and collaborators on mask former and variants. And mask former was mentioned in an earlier talk of this workshop as well. So I'm trying to give a bit of background of what we did there and how it worked before we shift back to video. Now, as I mentioned before, what we were aiming for is kind of a universal architecture. And convolutional neural nets usually have some form of backbone, some representation in the middle, and then some pixel decoder in order to retrieve back the semantic segmentation. What we added to this architecture was this transformer decoder that you can see in the middle of the slide here. It has on the left-hand side some abstract object proposals, which are in our case simply vectors that it uses as input and successively refines together with input obtained from the pixel decoder to eventually arrive at two outputs, one a class and two a mask. Now, importantly, this is binary masks for every object that exists, and there's a maximum number of objects that is determined by the object categories or by the abstract object proposals that are provided as input on the left-hand side. And for every one of those masks, there's also an assigned class label. And that allows us to use that architecture for both semantic segmentation as well as instance and panoptic segmentation. And in fact, we found that this type of architecture actually works remarkably well on all these three tasks: semantic segmentation, instance segmentation, and panoptic segmentation. We were surprised to see that we were able to get state-of-the-art on panoptic segmentation using respective data sets, on instance segmentation, as well as on semantic segmentation. And we did have a first version of mask former, which didn't do that well. And the 2 in mask 2 refers to using mask attention. And that's what really helped us get these additional performance improvements. Not only did it work on very specific data sets, we actually found that we were able to improve results across a huge variety of data sets, as well as across the tasks that I mentioned before. Now, here are some of the results that I already showed earlier that came from this mask2 former architecture. As I said, not perfect, but making mistakes that one could probably debate about. Now, why did this work? Or what was really responsible for improving the results? And I think work by Fortin and others actually showed why this works much better than we were able to show. What they were interested in is detecting these logs that you see in the image on the left-hand side. And what they identified was that if you use classic architectures like a mask RCNN, for instance, then the features that you get for a particular log are essentially averaged across axis-aligned bounding boxes, and that results in very confusing representations. Now, obviously, you could go one step further and you could take, instead of axis-aligned masks or bounding boxes, you could use rotated bounding boxes. And that helped them improve the results, as you can see in the second row of the table that I'm showing in the top right-hand side. But that only allows you to go so far. And by using these really abstract object representations as vectors, that allowed this mask former and mask to former architectures to really excel in these tasks. And they showed this on an impressively diverse set of images. And as I said before, they, in their work, were able to really much better show why mask to former works than we were. Now, how about applying this idea to videos? And in fact, what we found was that it's actually fairly straightforward to just take that architecture, you literally apply it to a video instance segmentation. And we didn't bother to write up a conference paper. You can find a tech report on arXiv. And we were able to actually get state-of-the-art results using this architecture. And there is one new work that is going to be presented by one of my students, Anvesa, at CVPR 2023. And she's also applying this to videos and now improving upon what I just talked about before, essentially making the argument that these simple object queries that we used back then are suboptimal for videos, and we need to include relative positional information and context, which helps then propagate these queries, which are represented with Q here in this slide, across the temporal domain. And the context gets increasingly augmented with additional information. Now, I'll not talk much more about her beyond encouraging you to stop by her poster to get to know more. She's one of the students that I guess started her PhD just, I guess, after COVID. And so it's her first conference presentation. So make it a memorable one for her. Instead, what I now want to go towards is looking beyond densely labeled video data, because as you might imagine, when we want to apply these architectures towards video, requiring to annotate all this data is just not meaningful. And this is work on X-Men, which appeared at ECCV 2022, and more recent work with collaborators from Adobe. Now, as I just alluded to, these end-to-end models that I just talked about, extended to videos, work reasonably well. They require to detect objects and temporarily associate object identities, but they're really hard to train because we need to annotate large amounts of data. And that is exacerbated if we're dealing with large vocabulary or even an open word setting. So these types of tasks are not really feasible. Yet people have shown remarkable progress with open word image models. I'm sure many people are familiar with the segment anything model or the segment everything everywhere all at once paper. And the question really is, how can we take these success cases that people have demonstrated and transfer these advances to the video domain? That's something that we're particularly excited about. And one thing one might come up with is essentially a mask propagation type framework, right? Can we propagate a single frame segmentation through an entire video? And if you think about it, about the problem from that perspective, then one thing that immediately comes to mind is techniques like video object segmentation, where we're given an image and the corresponding mask annotation for the first frame. And the task really is to then propagate the given information across the different frames in a video. And so essentially the task becomes, given an annotated object of interest in a first frame, track and detect these objects in the remaining frames. Obviously, this sounds somewhat simple, but there's a lot of challenges, right? Occlusions, videos should be arbitrarily long, lighting might change. And in fact, if you try many even state-of-the-art methods, we see that they start to struggle, particularly if occlusions are somewhat lengthy. And we really try to test this in the video that you can see here in the bottom right, where we took this Coca-Cola can and the Dr. Pepper can. I'm sure you know that both of them are red cans. We can bring them back one at a time, and the model actually is able to still understand which can is which. Now we can go even one step further, and we can hide the cans under this towel, then put it aside for a bit, and this happened roughly at the 1 minute mark. And then we can play around with the scissor. And in the interest of time, I'm going to do a fast forward here roughly to the 2 minute mark, where we're still playing with the scissors. So there is more than 1,000 frames between, I guess, the time we have last seen the cans and when we're going to remove the towel. And what happened was the model was still able to actually identify the cans correctly. Now, how did we go about achieving that? Well, one of the key aspects in these models is essentially some form of memory. And so instead of a simple mask propagation, what we looked into is memory-based mask propagation. So in general, we take frames, we memorize features from the first frame, we read then the memory to segment new frames. And then once we have segmented the new frame, we take this information that we obtained and write it back to the memory and keep on updating the memory. Now, using a single memory is, we found that to not be good enough. And we took inspiration from Atkinson and Schifrin, who hypothesized that the human brain actually has 3 types of memory architectures. It has a sensor memory, a working memory, and a long-term memory. So we try to incorporate something of that sort in a differentiable manner into a deep net architecture. I'm not going to go through all the details here, but these 3 levels of memory really allowed us to kind of distill information from like the pixel level into something more abstract that helped us to retain information and then achieve the results that I just showed on the previous slide. And giving a few numbers here, you can see in these 2 plots on the left-hand side, y-axis, Davis 2017 JNF, and over the x-axis, GPU memory increase per second, that the model that I just talked about, the XMEM model, achieves remarkable results despite very low GPU memory increase per second. In addition, in the plot on the right-hand side, you can see the JNF metric plotted for short-term videos on the y-axis and for long-term videos on the x-axis. You can see that the model or this memory architecture allows us to achieve roughly the same result, no matter whether the video is rather short or actually rather long. Now, obviously, while this is great, as I also showed before, this doesn't work that well if there is occlusions, and arguably I would say the occlusions are rather simple. So you can see, for instance, in the bottom left, again, the cat that I showed before, we often miss at least part of it, and in the roller coaster, we miss the roller coaster entirely. So what really is the problem? What are we still missing despite these memory architectures? And state-of-the-art methods, including XMEM that I just talked about, really use mostly a pixel level memory reading. And that's really prone to this low-level matching noise that you saw in the video before, and that I'm highlighting here at the bottom left of the slide. Right? The cat gets confused with other cats, or the method just doesn't really understand objects as a whole, so it doesn't understand objects holistically. So moving forward, what we're trying to do is a more object level oriented memory reading with a more top-down understanding. And here's a brief summary of what this looks like. And I hope you can see my mouse here. There is in green color, these 2 boxes, which are essentially the pixel memory and the pixel memory readout. And we're now combining this with ideas that I talked about before from mask to former. And adding these more abstract object memories and object queries into these architectures. And that really helped to actually improve results. And what we looked at specifically was the very recently introduced MOSE or MOSI dataset, which argues that it has heavy occlusions and frequent distractors. And we showed that by including these object level queries into these architectures, we can actually significantly improve the results without harming the frames per second of these models too much. And now showing the result complete, you can see the roller coaster again. And by having these object queries, we are able to maintain the roller coaster. And similarly, the cat that you can see in this video is delineated quite precisely too, I would argue. Now, one step forward, how do we now want to integrate this image level segmentation, for instance, from methods like SAM into these memory updates of video level or temporal mask propagation? And that's the second question that I want to briefly dive into. Now, classical approaches that use tracking by detection, they often detect the objects independently at every frame, and then they temporally associate them. Obviously, we could do something similar, which is process and use the memory independently per frame, and then we try to combine the results at the output. Now, the cons are that this is often very sensitive to the particular errors that you're going to run into, for instance, detection errors. And also, it doesn't really use the temporal information that is within these segmentation models. Now, what we are arguing for instead is a decoupled video segmentation approach. So instead of temporally associating the detected segments, we update the memory of the mask propagation for segmentation. So instead of essentially doing the operation at the output, let's do it at the input and store appropriate information within the memory before we then retrieve it. So these newly detected objects are added to the memory at fixed intervals. And then the segmentation simply just reads from the memory, as I described before, with these object queries, for instance. Now, new in our case means that the object has a small overlap with any existing object, so that allows us to recover and identify new objects if they appear. So you can think of the approach as being like an image is given, you run an image model, you update your memory, and then you continue using that memory, and eventually you reside and use both the memory and the new image model, and you merge the results into the memory as opposed to doing the merging at the output space. And the way we do this is via what we refer to as an in-clip consensus approach, where we run the image segmentation, where we propagate the segmentation from frames in a small clip onto a keyframe, and then we merge them in. And for that, we formulate a small interlinear programming, which combines the different segmentations into one that are then updated in the memory. And I know this is probably very abstract. I don't intend to go into more details here. If you have specific questions about this, please reach out. Happy to share some preprints in this direction. The results are summarized on this particular slide here, where we are evaluating on the open word burst dataset with common and uncommon classes. So in the table, you can see the numbers for both common and uncommon classes. And the metric is the open word tracking accuracy, OWTA. And as our image model, we use the mask2 formula that I just discussed beforehand. You can see that this merging at the input, this merging into the memory in the right way, actually improves results quite a bit compared to doing a combination more at the output space, if you will. And let me briefly show a couple of results of what this looks like in this video here. You can see the image input on the left-hand side. In the center column, you can see a baseline approach. And on the right-hand side, you can see the results of the method that I just talked about. And here you can see, particularly in the background, a lot of jittering of the baseline method, whereas this new merging into the memory allows to obtain quite stable results. Now there's maybe one more sequence after this one. The skateboarder. Yeah, there you can particularly see at the beginning the method struggling to maintain consistency across time, whereas by using this memory, we managed to get temporarily quite stable results. This one, I like that particularly because it shows really cluttered environments and really highlights, I think, the difference of baselines compared to using a memory with a proper or a careful merging of the results. Now let me show to text prompt video segmentation. One of the topics in this workshop as well, and similar to the results that I showed before here, this arcade sequence with the toy motorbike and the Wheel of Fortune. You can see that by using memory carefully baked into your architecture and carefully updated, you can actually achieve quite compelling results, and particularly also for this skaters here. Now, let me wrap up by summarizing that what we found to work well is to train large-scale image models on large amounts of data, and then to extend those to the video domain by using memory-based mask propagation. And two key ingredients are object-level queries for more holistic reasoning. That was the first part that I discussed. And then the second one is to do the merging at the inputs via something like a consensus algorithm before putting them into the memory. And then at the output, you just read from the memory. With that, I'm going to stop. Happy to answer any questions. I'm hoping to be at CVPR later this week. Try to find me there too if you have questions, or just feel free to reach out via email, which you can find here. Thanks to all the sponsors that made all this work. Happy to answer questions now.
A good list of sponsors. Right, are there any questions?
Hi, Alex. I have a question about the video data. As you mentioned, it's very expensive to annotate video segmentation data. So do you have any ideas on what are good video segmentation training data, and especially as evaluation benchmarks for video over categories? And also, I have a question about the metrics. So do you have any ideas on how to evaluate the segmentation quality that also
Could you either speak more closely into the microphone or someone repeat the question? I wasn't able to hear it. It was very noisy on my end. Sorry for that.
I just have a question about the data. So do you have some good video segmentation training data and especially evaluation benchmarks? Because it's very expensive to annotate video segmentation. So current data sets are all very small scaled. And also how to evaluate segmentation so that the metrics also considers the temporal consistency.
Right, great question. So I guess you're absolutely right that particularly for video data, dense annotations are very hard to come by. And that's, I think, what I try to emphasize as part of this talk is while we can afford to train image models on large scale data, maybe we should formulate or approach the video problem by these mask propagation formulations. Then you don't really need dense video data. You can essentially take any of the benefits that have been achieved on the image domain and put them forward to the video domain in a fairly straightforward manner. And in fact, that's kind of what we did in this in this work that I showed here. We essentially used refer former as a baseline. We didn't really develop anything new. All we did is we took refer former, which is an image model, and now combine it with this mask propagation idea to put it forward to the video domain. And that worked actually surprisingly well, and we were actually quite excited about the results. Now, to your second question about evaluation, if we don't use any annotations, it becomes very hard to evaluate it in a quantitative way. The one data set I would want to point out is I think I mentioned it on the slide earlier. There's the MOSI data set somewhere, which actually authors there spent quite a bit of time carefully annotating that data set. And it has fairly complex scenes. And that's also shown by state-of-the-art methods starting to struggle with that data set. So maybe one pointer I can put forward is, while I'm knowing that this is not, I guess, a solution to your question, is check out that particular data set. I think it's actually a good data set.
Thanks. So here you're using ILU, but I'm not sure if it's per frame ILU average. So do you think are there any better ways to evaluate video segmentation? So it also penalizes the model if it's not temporal consistent.
Yeah, again, great question. I do think ILU and FPS that we put here on this slide are very limiting metrics. You make two great points. Temporal consistency is something that we should evaluate more carefully, and we have actually not done that. But I'm sure if you look at, for instance, panoptic segmentation, right? There's also PQ and R, two metrics that you could multiply together in order to get the PQ metric. You could envision doing something similar on the video data sets in order to penalize, for instance, temporal consistency more strongly. That would be a first approach that I would go about doing that. That being said, we have not done that. It's a great suggestion.
Thank you so much.
Sure, thank you.
All right. Thanks for the questions. Thanks for the talk, Alex.
Thank you for having me. Thanks for the invite. Great workshop.
Another round of applause for Alex. University and then spent 2 years as a postdoc at UC Berkeley. His research interests span computer vision, machine learning, and computer graphics. He's particularly interested in image segmentation and understanding, with highly impactful works on fully connected CRFs, which, for example, won the Best Student Paper Award at NeurIPS 2011, or works on obtaining supervision from video games, and more recently on detection tracking. It's a pleasure to have Philip here today, share his thoughts on these topics. Please join me in giving a warm welcome to Philip Cranberry.
All right, sorry about the technical confusion here. All right, so today I'm going to talk about sort of a question we've had for a very, very long time, which was, should we use labels or should we not use labels? And the first discussions about this started actually when I was a postdoc at Berkeley. And I would say we actually, like as a field, we reached a point where we sort of have an answer, and the answer is going to be maybe a little bit of a letdown towards the end. But let me maybe preface, sort of start this talk by saying that in the past few years, we have seen an immense growth in large language models. And if I talk to my colleagues in NLP, they're really scared about this curve, at least the ones in academia. Like that just means that they can no longer train the models. They gave up control of their large language models, and they're paying OpenAI for tokens now. That's their research. And the sort of, I would say for vision, this is actually a completely different story. For vision, this is great because it allows us to answer sort of a very, very old question, which is sort of originated around the time of the gelato bit. And who in here knows what the gelato bit is? All right, Vito knows. All right, good. So it's back in Berkeley in 2014, Alyosha Efros sort of claimed that within a year, by 2015, unsupervised learning will do everything. There's no need for labels anymore. We will be able to train models in an unsupervised fashion, and we can just fine tune a little bit on whatever other tasks we need. And so the exact phrasing of the gelato bit is down there, just to be precise. Now, obviously, Alyosha was way too optimistic about this, and a year later, he paged Chandra Gelato. He bought Chandra Gelato, right? But this was actually just sort of the surface of a much bigger discussion we had back in the day, which was, should we use labels or should we not use labels? And sort of the two camps were pretty much Alyosha and some of his students on one end, actually very few of them, a lot of Alyosha students somewhere in the middle, and then Jitendra, Trevor, and the majority of all the Berkeley Vision people on the other end. And so the reasons to use labels back then were sort of, well, labels just provide a stronger supervisory signal. It's just sort of, they're there, we should just use them, they can supervise and train our models. Also, if we care about recognition tasks, which we did a lot in the early days of deep learning, the labels that we had from ImageNet, they really lined up well with our recognition tasks. So there was really no reason not to also use them for pre-training. And finally, sort of one of the bigger arguments that came sort of through time was it actually labels allowed for much better prototyping of new models. So if you had a new model, if you had unsupervised learning as your main mode, you now had to come up with metrics and sort of figure out how you actually say that this model is better. If you have labels, you just look at ImageNet, you look at the accuracy of the model on ImageNet, and that was it. Now, on the other side of the spectrum was the argument that, well, I mean, labels are sort of a very poor representation of our visual world. The world is rich and it's very hard to describe all the beautiful little details of the visual world with words, or even worse with categories, right? And also not every task aligns well with ImageNet labels. Like if you look at a lot of the geometric tasks, they have really nothing to do with the class labels that we had back in the day. And finally, sort of labels used to be quite expensive to obtain at a large scale. Now, if we go through this list, you can see that the arguments that we had to label actually didn't age very well. Labels provide a stronger supervisory signal. Well, in retrospect, it actually is not really true anymore. We have pretty good self-supervised learning methods. We have MAE, and they can reach sort of pre-trained models that are either at the level of labeled pre-training or outperform labeled pre-training. Labels match well with recognition tasks. Well, I mean, MAE showed that not using labels also does that. Now, they still enable faster development of new architectures. We might not everybody might do this anymore, but that's still sort of one that remains valid. Now, on the not to label side, there's really not much that's changed. Labels are still somewhat expensive to obtain. And there's a whole lot of tasks that are hard to label or where labels don't align very well with the actual downstream application. And sort of, it's true that we don't have a good way to describe all images with enough labels. Now here, I think, is where language models come in and where they can sort of help us also show that this side of the argument might not be that relevant anymore. Right? And sort of to show, to sort of drive home the point Alyosha made back in the day, just to sort of highlight this, he challenged us once to sort of take a picture of his office and try to describe everything in there with labels, right? Now, his office was famously a little bit messy at times, but it just shows that describing this image here with not move too far. All right, describing this image there with a ton of different labels is actually really hard. Like, even as a human going in there and sort of trying to figure out, well, what is this? These are some scribbles. If you're not a native English speaker, you might not quite know what this sort of outlet is or this sort of button there. And there's lots of other stuff that just lies around that's really hard to describe with words. Now, here's where large language models come in, and they really sort of change the field as much as anything in the past few years, I would argue. And the very first thing where we saw the power of large language models in computer vision was probably CLIP, where they used a gigantic data set of images with accompanying text. And this is just free-form text. They used the language model to encode the text into a fixed size representation, and they did the same thing with an image, right? And then they just trained it to sort of align language and text. Now, this is cool because for one of the first times in computer vision, we had a model that analyzed an image, but what came out was actually not a category label. It was not sort of dog, cat, or some boring label. What came out was a free-form sort of text description or an association with a free-form text description, right? And now, all of a sudden, anything that we could describe with words, we could associate to an image. Now, we could do the same thing with detection as well. So we can go and not just describe entire images with language, but we can now go in and describe different objects that we know with language. And if you look at the sort of setup of a standard object detector, usually an image goes in, there's some detector, has an encoder, has a decoder, it produces a bunch of candidate detections, usually such as boxes with associated features. And in the end, we just classify each of these boxes into a fixed set of classes. Now, if you think of upgrading this to use a language model, well, the thing you do is you simply replace the categories up there with embeddings of the words that describe your categories, right? So it's a very simple change. So instead of using a fixed size learned feature vector for, let's say, bear or cat, now you're going to go and just embed this bear or cat description in with a language model, and you use the output of the language model, and you use the dot product between that and the feature of your box, and that's now your detection. That's the score of your detection. Right? And so this idea predates CLIP by a few years. This has been upgraded to use CLIP. And not sure if actually, I think I have the year wrong down there, but it has been upgraded to use CLIP in two ways. One is use the CLIP word embedding here, and then the other is to use the image encoder of CLIP itself to embed all the images, or to parse the image that you then go use in your detector. All right, well, so how well does this work? This is not the actual paper that I presented, but this is our reproduction of this. If you go, maybe one thing to mention is you obviously have to go and train these models. And the way you go and train these models is use standard object detection data sets. And if you go train these on standard object detection data sets, and now ask the model to detect what this lion here is, it will first tell you, well, this up here, this is definitely a dog. This down here is or this over there is a cow. This is a pony, and this is a bear. Okay, so what's going on? Well, like, we just have this most powerful model that can reason about all the concepts that we'd imagine, and all of a sudden it just produces sort of weird results, right? Well, what's going on is that the data sets we use to train the actual sort of detector, not the data set we use to train the language part, but the data set we use that we train the detector on. If you look at Coco, it does not know about lions at all. If you look at Elvis, you get about 43 lines in there. And that's just simply not enough to learn about the visual concept of lions, right? And so we now have these architectures that are in theory all powerful and could reason about any visual concept that you could put words to, but we don't have a good way to train them. All right. So if you go back to the argument, sort of to not label, we have the architectures that could describe the visual world in as much like that, in as rich of a sort of as rich of words as we can imagine. We could have labels that align to anything that we can put words to, and they could even, like, if you can actually obtain them at scale, they could even be relatively cheap to get. But we don't have a way to train these models. And so that brings us to sort of a work we presented at ECCV last year, DETIC, where we looked at how do we train these very flexible and powerful detection models that use language to guide what you want to detect. And so the model we looked at is we use the CLIP embeddings to embed words of sort of category names into word embeddings. Now, we don't use the CLIP image encoder. It turns out the CLIP image encoder, it works quite well for full images. Using it for detector has some issues, and it's much better to just train a detector from scratch. All right. So we train a detector from scratch, and the only thing we do is we replace categories, sort of the feature vectors we have for categories, with word embeddings of categories. Now, if you just train this on Coco and Elvis, you'll get the same detector that does not know what a lion is. All right. But what we also do is we use ImageNet, and we use the 21,000 categories of ImageNet as a supervision for this detector. And so the way we'll do this is for anything that has a bounding box annotation, meaning Coco and Elvis, we train this just like a regular detector. So we have the detector predict sort of in an image, predict bounding boxes. We compare them sort of to the ground, or match them to ground truth bounding boxes. We use regression to refine the location of the bounding boxes. We use classification to improve the classifier or the sort of the scoring function of the detector. Now, for any image that does not have box annotations, what we will do is we'll first go and predict a bunch of boxes. All right. And so there might be a box that's sort of this size. There's going to be maybe a couple around the bears. And then we'll select one box in the image, and will use the ImageNet label, the label that was associated to the entire image and associated to that box, and train just the classifier. All right. And so the trick here really is to set up a very dumb weakly supervised learning method. But if you do this at scale on a large enough data set, it actually doesn't matter how dumb it is. It turns out if you just select the largest box the detector outputs and just assign the label to that one and say, this is the ground truth, this here, this is the bear. The model itself, the deep learning model, is actually clever enough to change its decision boundary enough to adjust to all the classes that exist in ImageNet. All right. Now we took a detector that was able to reason about classes that we have bounding box annotations for, but it can now reason about anything that you could put an ImageNet label to. Right. And here are some examples. So we have a demo online where you can sort of feed in an image, and you can feed in a bunch of terms of like objects that you might be interested in. And it will give you an instance segmentation of sort of a free form set of object categories that you can think of. Now, this is actually, if you ever want to build a demo, this is a great trick to build a cool demo. Ask the users to provide you with the categories. If you have to come up with the categories, it's actually quite hard and it doesn't look very magical. But if the user enters a bunch of categories and you find these categories in the image, all of a sudden things work very, very well. Here's another example, and these are sort of images that people on Twitter download or like used our demo and sort of just tried it on various different images. And it works really, like it works remarkably well. Like you can just have free-form text now, and you can find you can sort of online build this detector that sort of takes these free-form text classes and detects anything of this, any of these free-form text classes. All right. In terms of numbers, it also works quite well on sort of the Open Vocabulary Elvis challenge here. Here are the results of DETIC, and you get a sort of a few point boost over the baseline, which was just supervised trained Elvis. The baseline we compared to, this is a paper from Google. It used a slightly different backbone. That's why the numbers are a little bit lower than our baseline. All right, now can we do better? So this far, I've shown you a detector that learns to detect or to find objects. And then in the end, we simply just say, you can name these objects anything you would want, right? But there's something a little bit weird about this setup. If we train this detector on Coco and Elvis, well, it is going to be very good here. This part is going to be very good at finding Coco and Elvis classes, right? It might not be very good at finding some arbitrary new class that it just came up with because it never learned to detect them. It learned to label them once it found a detection, but it didn't learn to detect them. And so in a paper that's hopefully going to be in archive soon, we flipped things around a little bit. So instead of feeding in the labels at the very end, we want to see, can we build a detector that from the get-go is conditioned on what language or what sort of classes it is going to detect. So instead of feeding in the language model or the language embeddings after the detector, we now feed it in after the backbone of the detector, and we use a query-based detector. And for each of the queries, they're now sort of conditioned on the outputs of the language model or the vectors of the language model. So if you want to reason about bears, we'll produce some queries that specifically look for bears in this image. Now we train it exactly the same way as we train DETIC, and the results are quite encouraging. So if you feed in the language model before the entire detector, you can gain about 2 to 4 points depending on what metric you look at. Right. Now, we also extended this to video models. And here we look at just video understanding and sort of associating entire videos with language description of these videos. And this is a very similar setup to CLIP, where we have text encoder here. This should not be text. This is video encoder here. So you have a text encoder, you have a video encoder, and you embed these two things into the same space. They have a contrastive loss that sort of forces videos with associated text to sort of embed into the same space, and videos with any arbitrary other text to embed into a different part of the space. Now, one of the issues with sort of learning video language models is that the annotations we have are relatively sparse. You're not going to be able to get a description of every single frame in a video. And you're also only going to, like at scale, you're only going to get sort of one, maybe two descriptions, maybe three descriptions for a small set of videos. And what we did for a paper that's going to be presented at the CVPR is we really looked at how can we make this description much, much denser. And there's two ways we are doing this. One is we're interpolating in time, and that is if we have, let me use a different color. So we have sort of ground truth descriptions provided by a user. We now just ask a language model to build a coherent text description out of the sentences that we got as an input. Sort of, we just tell the language model, hey, this is the first sentence, this is the last sentence, now build a longer paragraph of text out of it. And we'll use that to supervise frames that are in between, right? So for any frame that we don't have human annotations in between, or for every sort of short clip that we don't have human annotations, we'll now just use outputs generated by a language model. The second thing we're doing is we're looking at these human annotations, and we're just asking the language model, hey, can you paraphrase this? Can you paraphrase the language that was described here just in a couple of different ways? And so that gives us a lot more supervision to train a very large vision and language model. And in general, once we actually have this works quite well. So this is a zero-shot evaluation on a large number of sort of video action recognition or video recognition data sets. And for the majority of them, or like all of them, we beat this previous state of the art, which is trained specifically for one data set, or specifically sort of for a subset of data sets in a zero-shot manner. We beat them by a fairly substantial margin, anywhere between sort of 4 to 5 points for most of them. Right? Now, one issue with this work is that it is very, very large. So if you look at sort of the number of sentences that we had to produce, number of video clips that we had to consider, this is something that we could only do in collaboration with Meta. On our university computers, we couldn't train these things. This took, I think it took 64 A100s, several days to get the model. All right, and then there's dedicated machines that sort of decode the video, dedicated machines that sort of pipeline all the data in. Okay, this is a huge engineering effort. And Meta will just throw the money at it because they can use it for their advertisement. Now, what we did at UT, which is also hopefully going to be an archive soon, is we showed that we can actually still train these models very efficiently on university hardware. And so there's sort of 3 tricks or 2 main themes that we had to do to make these models more efficient. Number one is we had to reduce the amount of memory they consume. And the tricks here was just using flash attention and gradient checkpointing. And that got the memory down by like not quite an order of magnitude, but close. The other thing we did is we had to fuse the way we decode videos. So usually the way these models learn about videos is you decode a gigantic video and then you crop a small part out of it. Now it turns out that most modern video codecs can actually directly decode a small part out of the video. This is called a cropping filter in these decoders. And if you do that, you can make I/O fast enough that you can run I/O on the same machine as you train your model on. And so what this means is that we can now train these gigantic video models, these gigantic video language models, instead of sort of using 32 or 64 A100s or V100s, we can train them on 8 A5000s. And A5000s are like, they have less memory, they're much worse in terms of sort of compute than the A100s, but we can do this in a lot fewer GPU hours. So we can reduce the number of GPU the compute you need by about an order of magnitude. And the other fun thing is it actually gets better. Just doing this more efficiently got better because we actually trained for longer, even though we sort of are training for much shorter. The actual number of sort of gradient steps we could take if you optimize this is larger. The same here. There's another fun comparison if you look at CO2 produced. We're I think over 90% better. We have over 90% reduction in CO2 just because our cards consume less energy. Yeah, and so this did also fairly well in the Epic Kitchens challenge. So if you're interested in this, you can look at go look at the challenge tomorrow. But in general, sort of this sped up version of this works quite well. All right. Now let's go back to the original premise, which was sort of, should we label or should we not label? And I already mentioned that sort of the camp to label, there was only one sort of argument left, which is, yeah, maybe it makes our development cycle slightly faster. Now, if we look at what what sort of these vision language or what language models did to vision, it really got us away from labels. Like we no longer need to use labels. We can just use language embeddings, right? Now, maybe Alyosha would at some point rail against language embeddings, who knows? But the whole argument not to collect labels is gone because of these because of these language models. Because we now, anything that we can describe in language, we can detect, we can recognize, we can work with in our vision models, right? So sort of this argument is gone. This argument is gone, and that labels are too expensive. I mean, we showed that we can actually get by with the data sets that we have, the labels that we already collected, and learn good vision language models from those. So with that, I would say the debate is probably finally settled, and it's sort of pointless to argue about not use labels or not use labels, because by now we'll all use vision, and we'll hopefully soon use all language embeddings and language models to supervise things. And in conclusion, this is, by the way, this is Alyosha's office, fully labeled. This is sort of with all the text, all the labels that you could probably find in his office. And I'm happy to take any questions if you have any.
Thanks for the sharing. Detector is a very insightful work, and it inspired many following work. And I have a question about open vocabulary object detection evaluation. We always use LAVIS as a evaluation benchmark. Do you have any idea about the future of open vocabulary object detection evaluation? Because LAVIS is still a human annotated predefined category dataset. I can ask more generalized. What do you think about we evaluate not labeled method using labeled dataset?
Yeah, that's a very good question. And I think there's really, it boils down to, do we pretend like that we knew the labels of Elvis, or do you pretend that you didn't know the labels of Elvis, right, when you trained the model? And I think if we live in a world where we pretend like that we didn't know what labels we had to consider, then I think Elvis is an okay benchmark. It's probably one of the better ones we have. Evaluating something that we don't have labels for, or like don't have text descriptions for, and doing this in a sort of an unbiased and fair way, I feel like it's very hard, and like I don't have a good idea on how to do that, and I'm very open to like people telling me about ideas on how to do that. Yeah.
Okay, thank you.
Mm-hmm.
I had a question about the sample efficiency of Decola. So one of the key ideas that you do the vision language embedding before the entire detection pipeline is finished. And one thing that struck me about the example about the predecessor Decola was that if you train it on Coco, it would, sorry, if you train it on Elvis, there are only 43 lion images and it couldn't recognize lions. Humans are much more sample efficient. Even like a baby, show it to zoo and show it crocodiles and you're like, what is that? They're like, it's a dog. And you're like, no, it's a crocodile. And then they never make that mistake again. So have you looked into whether Decola is more sample efficient than its predecessors? That if you train it on Elvis, it can actually like recognize lions?
Yeah. We have looked at that part of sample efficiency, but the trick here is actually, so Decola, it injects the language labels essentially into proposals. And that turns out to work much better if you do weakly supervised learning. So we haven't looked at sort of if you have just small number of detection labels, do you do better? But if we train a detector, and we always have to sort of pre-train Decola using sort of a fixed set of language labels. If we use that and then look at how well it would work for weakly supervised data like ImageNet, that works much better. And it is able to localize objects. We no longer need to play this ugly trick of let's just use the biggest detection. We actually just use self-training there. And so in that regard, it is somewhat more sample efficient at getting a better proposal work. But it's hard to say if this actually translates into a more sample efficient detector.
Gotcha. Thank you.
Yeah.
For the decode, I was wondering, open vocabulary detections right now, they focus on yes, new categories, but the category names are still one word, two word descriptions. I was wondering if decoder like encoding used earlier into the detector would also help in detecting more descriptive objects, like first with
Yeah. Yeah. So for the people on Zoom, the question was if you use Decola, so if you inject the language embeddings sort of earlier in the detection process, would that help us get more sort of interesting text descriptions of language and not just labels that we translate into text embeddings? The short answer is, again, we haven't quite looked at this just because it's hard to actually find them. Like it's easy to find them on an image level, but in the very first stage when you go and train your proposal network, it's actually very hard to find boxes that are somewhat localized in an image with good text descriptions. It might be okay to do this in a second phase if you go and fine tune your proposal network as well.
Yeah, thanks for inspiring. I also have a question about the detection. Actually, you propose a very interesting pipeline. You separate the detector and the classifier into two parts. We deep learning guys do the end-to-end training and we divert from this pipeline for a while. We create our system, the software use this modularization view, but we do the deep learning system in an end-to-end style. Do you have some insight, or did you do any experiment try to find out why the detector can generalize to some new classes? For example, is it based on some low-level features, for example, the edges or the patterns, or is it because of the generalization ability brought from the deep neural network? For example, it can generalize from the cat to the line. Have you do any related?
Okay. Yeah, that's a very interesting question. And I mean, clearly the generalization ability cannot come magically, right? There's two sources in which we can become more general. Number one is language. The language model itself can actually generalize, right? Like it can probably like associate cow and cattle as sort of similar words that will be detected in the same way, right? And so in that manner, it will generalize to similar descriptions of the same concept, right? And I think for anything else, it's quite hopeful to assume that the detector will somewhat magically generalize. I think if you had data, image level weakly supervised data, then you could see how this generalization can happen, which is sort of let's say the cat and lion example, right? Let's say you tell the detector there is absolutely a lion in here. It doesn't have a good lion detection, but maybe cat and lion are somewhat close together in a language embedding, and then you will learn to adjust and do this. But without any signal, I don't think there is going to be generalization. I don't think you will ever flip from a cat to a lion detector just because you changed the input word description. It has to come through some sort of supervision.
Okay, thanks. And a following question. In this pipeline, we also see a maybe new path, a new future. Actually, we don't need an end-to-end data set. For example, we can have two unpaired data set, one just for detector and the other for the classifier.
Yeah.
But we actually need a protocol. How can we pair such unpaired two data set? Do you have any insight or ideas on this? How can we find such kind of good data set that can be used one for each? We can use each data set for each part of the neural network training.
Yeah, I mean, I think the only thing I can say is you should probably, like, the protocol should just be, we use this data set. That's what we currently do. We use these set of data sets to pre-train. And then I think that the important part is that it's standardized around an evaluation, right? And that you make sure that sort of there's some separation. Like if you want zero shot, maybe you shouldn't have the concepts in your data sets. And that you compare sort of under compatible conditions. But I don't think it's necessary to set up something more than just sort of, these are the data sets we use, or these are the data sources we use, and this is the standardized evaluation protocol. That's at least from my point.
Okay, thank you very much.
Thanks again. Thanks for a great talk. Let's thank all the speakers again. Thanks, Vito. Alexander Spring, your talk.
Yeah, you could.
Workshop. Thanks for the invited speakers. Thanks for the participants for the challenge. Congratulations to the award winners again. Thanks for everyone for participating today. All right. Thanks. Thanks for organizing this. Thanks for talking. All right. Well, see you later. See you later. Yeah. Thank you.
It's very funny. Yeah.